Yes, madam.
Well,
Yes, madam. Tell me.
sir, am I audible?
Madam, you are audible.
Okay. Good evening, one and all present here. I'm Shweta, Assistant Professor, Department of Electrical and Electronics Department. Thank you, participants, for joining us today. I welcome you all for the day 3 of Faculty Development Program on Power Electronics Applications in Microgrid using AI. Today we will start with the session 5 entitled with the topic Modeling and Control of Power Electronics Converters for Smart Grid Systems. I'm glad to introduce our speaker for the sessions, Dr. G. Ilirajan sir, Professor and UG Program Head, Department of Electronics and Electrical and Electronics, Jain University. Dr. G. Ilirajan sir obtained his BE degree in Electrical and Electronics Engineering and ME degree in Power Electronics and Industrial Drives from College of Engineering, Gundi, Anna University, Chennai. He has obtained PhD in Renewable Energy Systems from SRM University. He has 22 years of combined experience in academics and industries. He has attended many national and international conferences and has more than 30 publications in Scoopus Index journals. He has published 4 books and has completed 2 funded projects sanctioned by MHRD, Government of India. Dr. G. Ilayarajan sir is a certified teacher in innovating teaching methodology from NITTDR, Tharmani, and also a Government of India certified solar PV system designer and project manager. He is a certified internal quality auditor for ISO 9001-215 quality management system. We welcome you, sir.
Thank you, madam. Can you hear me?
Yes, sir.
I take this opportunity to thank the JAIN management, uh, President Bandari sir, Hariprasad sir, the organizer of this event, that is coordinators of the event, Dr. P. Kishore Kumar and Dr. Tripti N, for giving me this opportunity to deliver today's lecture on modeling and control of power electronic converters for smart grid system. Okay, this is Dr. G. Ilarasan on behalf of Department of Electrical and Electronics Engineering. I welcome you all to the ATAL Faculty Development Program on power electronics applications in microgrid using AI. So today, the topic is modeling and control of power electronic converters for smart grid systems. So there will be people who will be not knowing power electronics. Okay, basics of power electronics. How many of you are there like that? Can you raise your hands in the chat box or a raising hand? Use the raise hand option. Yeah, Chandrasekhar BM. Nagaraju. Okay. Muktayati. So I can see totally 45 participants in all. Shweta BN. Okay. Oh, many people. So there will be people of mixed qualifications. Because without touching power electronics, if I go into this subject, okay, you may not understand what I am dealing with. Okay, first thing. Second thing is, today I am going to give only some guidelines to the modeling and simulation. I am not going to do any show any simulations, or I am not going to practically show any simulations. I am going to show only the circuits, power electronic circuits that is latest used in microgrid technology, and some controlling technology. What controllers, what you can use for your work if you are going to proceed with microgrids. Okay. So based on this, I have framed the contents as: first we will see what is smart grid by definition, then what is power electronics, then role of power electronics in smart grid, then we'll go to DC-DC converter simulated results, then active front-end rectifier simulated results, control methodology, inverter configurations, right? And inverter configurations, control methodology. Okay. So we are going to deal with 3 converters, that is DC-DC converters, then active front-end rectifiers and inverters in power electronics. Let us see what is a smart grid. It is an electric grid of future. Okay. Because day by day the oil is becoming scarce, we have to go for alternate energy generation. So when we go for alternate energy generation, then we have to attach them with the conventional generation, what we are having. Okay. So in this scenario, we need smart grid. Okay. So smart grid and microgrid are differ only by a very small difference. Smart grid means you can understand it is intelligent. Okay. Smart grid is intelligent. Microgrid means small. Okay. Smart means intelligent grid. Microgrid means small. It means, yeah, smart grid may be small or may be big, but it is intelligent. Okay. It means it can sense troubles within the grid. It can solve issues within the grid. Okay. It can take actions within the grid. Okay. When the grid is self-healing, it means something happens to the grid means, okay, instead of going out of sync, that is failure, instead of failing, the smart grids will take constructive action that will result in avoiding grid failure. Okay. That is one thing, right? When you go to microgrid is small. Suppose we have a layout, say ISRO layout is in Bangalore. Okay. So ISRO layout is a place where people belonging to ISRO, they are staying. Okay. Let us say it is a colony-like arrangement. There they want self power generation. Okay. So they make solar panels on each houses, right, of the ISRO layout, and they want to distribute the energy among themselves, means, right, that becomes a microgrid. Okay. That may depend or may not depend with the electrical grid, which is outside, that is Bangalore State Electricity Board. Okay. So now you can see on one side power generation, on middle transmission and distribution, on the other side it is the power storage and consumers, which constitutes a smart grid. So it means smart grid, in smart grid power flow will be monitored continuously. So what is smart grid by definition? The smart grid enables better demand response, quicker detection of outages, more efficient use of renewable energy sources, and improved overall system management, providing a more flexible and resilient energy infrastructure. Okay. Slowly, all the conventional grids are becoming smart grids due to the advancement in the technologies. Okay. Introduction of artificial intelligence. Okay. All these things is bringing, making the conventional grids into smart. So it means some 20 years back, if we take, there will be lot of power failures, right? What are the difficulties we used to face is one is power failure. Okay. Another one is power fluctuation. That is quality of power. Okay. Quality of power used to be very poor. Right. It used to fluctuate. Right. No one used to get proper voltage. Okay. 220 volts means 220 volt never comes to any house. Okay. There will be a lot of drop. Okay. Similarly, frequency variations will be there. There will be sometimes high voltage coming into picture and spoiling the equipments. Okay, all these things have been overcome. Today, if we take Indian energy scenario or Indian power supply system, we are up to the international standards. It means our voltages are maintained perfectly fine within 1%. Frequency is perfectly maintained within the international standards. Okay, so so only you can see as of now, right, the power failures have reduced. Unless there is a big rain or thunder showers, power doesn't go off, right? That is one thing. Second thing is power quality has also improved. Okay. So smart grid, it is an advanced electrical power system that uses digital communication, automation, monitoring technologies. So it is a electrical power system which needs communication first, automation and monitoring technologies. So it optimizes the generation, distribution and consumption. Smart grid also integrates sensors, smart meters and real-time data analytics. Okay. An example of real-time data analytics are smart meters, right? You can go to your house, open the main box, and you can see a digital meter which is fixed in this main box. There, previously, some 10 years back, there was a meter which with a disc that is rotating and numbers displayed. Only we can see these two. There will be disc rotating and there will be a number moving. Okay, according to the disc rotation. Other than this, there was nothing available for the consumer from the electricity end. Today, you can see digital meters being fixed. What and all you can get inputs you can get from the digital meter. Can anyone tell from the audience? Open your mic and tell from today's digital meter what and all the parameters you can get. Can I call? Can I call the name?
So voltage, power, current, power factor,
Place consumption.
temperature.
Okay, right. So first thing will be displayed is a date and time. Okay, then kilowatt hour, that is unit of electricity. Then voltage in each phase of supply. In all houses now it is three-phase supply. In each phase, what is the voltage, and in each phase what is the current. Okay, what is the active power drawn, what is the reactive power drawn. Okay, what is the demand. Okay, power factor. See how many parameters. Okay, so is it not the improvement of technology? Right, we have been given lot of inputs. We are getting lot of inputs from a simple meter in your house. Means what and all they will be having, right, in this smart grid control. Okay, you have to appraise that. Okay, so this enhances the efficiency, reliability and sustainability of the grid. Okay, now we go to power electronic converters. Seeing this block diagram, can anyone say what you infer from seeing this block diagram? Give your inputs. What and all you get from this block diagram? Yeah, open your mic and speak. Nirati Siddiq.
So for the control unit, we are giving the input as reference, and from the output, we are getting the actual data.
Okay.
If it is not matched, then the control circuit will give the proper signals or proper information to the IGBT, which is
Okay,
a
okay.
switch.
I can get you, Nirati sir. Right. Thank you. Any other answer? Any other observations? So this session should be interactive. You call Basavarajappa? Yes, sir. Are you there? BVSV Prasad. Can you answer? K Chitra, Dr. K Chitra. Amit Atri. Can you answer this, what I have asked? Hello?
Sir, why input is taken in the control circuit, that we don't understand. Normally, it is not considered in control circuits. No?
Yeah, I'll tell you, right? Okay. So from this diagram, what I observe is the input may be AC or DC. You don't bother about the input. Okay. And the load may be AC or DC. Right? You don't bother about load. The input can be anything, AC or DC. Similarly, the load can be AC or DC. Right? This input and output can be very suitably matched with the converter, what you see in the middle. So what we have to select, no, right? So in conventional electrical engineering, right? If it is a DC motor, we have to select DC supply. If it is a AC motor, we have to select AC supply. Okay. If it is a 220 volt DC motor, then we have to select 220 volt DC supply. If it is 415 volt AC motor, we have to select 415 volt AC supply. Okay. This is no more required. Okay. The input can be anything. The load can be anything. The thing what we put in the middle in the form of converter will match the input with the output. Okay. Right. So for that only, for that matching only, we get a line from the input and we give to the control circuit. Okay. We need, suppose if it is a AC supply, we have to get the zero crossings of the AC waveform. Okay. So it means zero crossing from the supply. So based on the zero crossings only, we can trigger the firing pulse. Okay. For that purpose, we may get, that is the answer for your question, ma'am. Right? Okay. So
yes, sir.
Yeah, it is a matching, right? Marrying a load with the source through the converter. Okay, did you understand? Okay, so it means what and all changes it has done. If you see, traction means electric train means in olden days, right? Only DC series motor can be used. No other motor than DC series motor can be used for electric traction. Today, slip ring induction motor I can use for electric traction. I can use AC motors for electric traction. I can use any motor for electric traction. Okay, that is because of this power electronic converter, right? So you can see one important thing, right? Note down input. After that, switches, IGBT, MOSFET, and peripherals. That is a converter. Then there is a filtering circuit. Okay, filters are required. filtering circuit, and then there is a load connector, and the feedback is taken and given to the control circuits. User interface will define what you need. Okay, so you can give the input through user interface. Rest of the things will happen automatically. This is the block diagram of the power converters, power electronic converters. So power electronics, the role of switches, let us see. So it involves a use of semiconductor devices such as transistor and thyristor as switches to control the flow of electrical energy in various forms such as DC, AC, or combination of the both. So power electronics is nothing but using switches. The use of switches, there will be, you have to take some switches. It can be SCR, it can be transistor, everything, and you have to arrange them in a fashion. Okay, and you have to turn it on and turn it off. That's all. Okay, you take a switch, connect in a circuit, turn it on and turn it off. Okay, rest of the things, the configuration will take care. So example switch, if you ask me, example for a switch is SCR. Okay, you can see a SCR on the right hand side. You can see bigger SCR, which is used for energy transmission, HVDC systems and all. Okay, it has cathode, anode, and gate. The symbol is similar to that of diode. Only thing is there is a control called as gate. So you can see here SCR thyristor symbol. Okay, so the diode and SCR share the same symbol, except that there is an additional terminal called as gate for the SCR. Okay, it means this is the control, right? So with this control, what we can achieve is what I am showing in the next slide. You can see diode and SCR, both circuits are rectifiers only. The first one is diode rectifier. The second one is SCR rectifier. Okay, right? So I can see here, both are off wave rectifier, right? So first one, you can see only positive off cycle is rectified, negative off cycle is not rectified. Okay, but positive off cycle is fully appearing in the output. Okay, as a DC voltage, right? Whereas here you can see, out of positive and negative off cycle, only positive off cycle appears in the output. Okay, that too only a part of the positive off cycle is appearing in the output, right? Okay, this is what the control or gate does. Okay, even though this SCR is eligible to conduct through the entire positive off cycle, okay, you can turn it on at any time during the positive off cycle. Okay, at the moment you turn on, from that point only the SCR will start to conduct. Okay, and during negative off cycle, even if you apply the control signal to the gate, okay, the SCR won't turn on because it will be reverse biased. Okay, so biasing is similar to that of diode, right? SCR also is forward bias and reverse bias. Diode is also forward bias and reverse bias. So diode will automatically conduct from 0 to pi, whereas SCR conduction can be controlled from 0 to pi, right? So according to the control, you will get the output voltage, right? You can see the comparison between a diode rectifier and a SCR rectifier. Any doubts in this? Anyone having any doubt? Okay, we'll proceed. So what is the role of power electronic converters? Power electronic converters simply change the shape of the input waveform according to the requirement through switching action. Power electronic converter doesn't do anything, right? It will change the wave shape. Okay, it will work on the waveform. Power electronic converters work on the waveform, input waveform, and it will change the shape. Okay, so according to the waveform shape, what we obtain, right, we get different types of voltages and current. Voltages, right? Different type of voltages mainly. Okay, for this arrangement, that is waveform changing or waveform conversion, we require switches. That switches are nothing but transistor, SCR, all those things. Plus, we require a control pulse generator, control pulse. That is, if it is a transistor, we have to generate a base signal and give so that the transistor will turn on. If it is a SCR, we have to control, we have to generate a gate signal and we have to give to it. Okay. The signal may be current or voltage. Example, if it is a BJT, it is base current. Okay. If it is a MOSFET, it is gate source voltage, VGS. Voltage will be the control. Okay. In case of MOSFET, in case of BJT, it is current. So a control pulse is a current pulse or a voltage pulse. Okay. That depends according to the switch. Whatever the switch requires, right? And the amplitude, magnitude, and all will be decided by the individual switch. Okay, suppose BJT we are using, that BJT is going to will require 10 milliamps of current to switch on. Then we have to supply the gate current of 10 milliamps, then only it will switch on. Similarly, a MOSFET is going to turn on only with a VGS, that is gate source voltage of 10 volts. Then we have to supply 10 volts, then only the MOSFET will turn on. Okay. So what you understand from this power alternating converter, it is nothing but waveform changes, right? Input waveform changes. For changing the waveform input, we require switches. For controlling the switches, we require a pulse. Okay. So once we have all these things, we can convert AC to DC, DC to AC, DC to DC, and AC to AC. Conversion is possible. Okay. Any doubt in this? Okay. Thank you. If you have any doubts, you just instead of raising hands, you can open your mic and ask. So types of power electronic converters. Right, if you see, AC to DC conversion is called rectifiers. All of you know this one. DC to AC conversion is called as inverters. This also many people know. DC to DC conversion is called choppers, right, or DC-DC converters. Then DC to AC conversion is called as AC voltage controllers, or AC choppers, or cycloconverters. Okay. This AC to AC conversion alone is very much supported by an equipment which has the highest efficiency. Hello? Someone is speaking. Yeah. So AC to AC conversion alone has a support. Okay. When compared to all other conversion, AC to AC conversion alone has a some form of support. Okay. By an electrical equipment, which is a best invention is electrical engineering, that is nothing but the transformers. Okay. So since transformers are there, AC to AC conversion is required at certain levels only, right? Okay. Even in power systems, you can see they use only, even till today, they use transformers only for stepping up or stepping down voltages. Okay. Right. So it means we have to mainly see power electronic converters. Mainly we have to see only these three things: AC to DC conversion, DC to AC conversion, and DC to DC conversion. Right. Now for the people who are new to power electronics, okay, we'll see first AC to DC conversion. Okay. So AC to DC conversion, the converter, you can you can see two switches, T1 and T2, connected in a circuit. This is the converter. What this converter does, you see in the right hand side, the conversion, what is happening. You can see a input of 220 volt AC. Okay. Full sine waveform you can see, right? You can see a output of 220 volt DC you will get. Okay. If you are going to use the entire waveform. Okay. If you are going to use entire waveform, you are going to get 220 volt DC. It is a full wave converter. Okay. Both positive cycle and negative cycle are utilized. So you can see what this converter is doing is, it is clipping the negative half cycle of the input waveform and pasting it in the positive side. Okay. The negative half cycle is cut and pasted in the top. Okay. For every cycle, the negative half cycle alone is pasted in the top. Okay. When you do that, what will happen is all the cycles now, off cycles become positive only, because everything is above 0, right? And the input voltage 220 volt, right, without change in area is appearing in the output. It means I am giving 220 volt AC input, I am getting 220 volt DC output. This I will get as a result in diode bridge rectifier also, okay, or in a thyristor rectifier, what I have shown here, with 0 degree firing angle or without control, 0 degree control. I turn on at 0 and turn off at pi. I'll get the entire off cycle. Okay. So this will be the output. Suppose you want control. Okay. So I want only 110 volts. So I have brought one device from America. Okay. Which needs only 110 volt DC. Right. Whereas here we are having only 220 volt AC supply, but I want 110 volt DC. What I will do, I can very easily control, right? So you take the input waveform, right? You trigger the devices, or you control the devices T1 and T2 only when in the middle of the input, that is AC, right? So when you do that, you can see from 0 to 90, so 0 to pi means 0 to 180 degrees. Okay. So from 0 to 90 degrees, you don't switch on this thyristor T1 and T2. After the supply reaches 90 only, okay, you switch on the power to T1 or T2. Then what will happen? The rest of the voltage will come, right, in the output. You can see only half of the input is appearing. So half of the input is appearing means if it is 220 volt, the output will be 110 volts. Okay. So this we have to take and we have to use it. From this, what you can infer is the waveform, input waveform is, the shape of the input waveform is changed. You can see output 220 volt DC is like this, right? If it is 110 volt DC, it is somewhat like shark fin. You can see somewhat like shark fin, right? It is like this. So it means this is not DC. DC should be a straight line. Okay. If it has to be straight line, then we need filter. Okay. So this supply, this output waveform should be given to a filter, right? So if you want a voltage filtering, you have to give it to through a capacitance connected in parallel, okay, across a load. And if you want current also should be filtered, then you have to attach L, right, inductor in series, right? So if you want both current and voltage to be filtered, right, then we have to attach LC filter. Okay. When you give this supply 220 and 110 to the filters, then it will make it as a straight line or a ripple free output. Okay. Or a perfect DC. This is AC to DC conversion. Now we go to DC to AC conversion, right? Okay. So you can see the converter. This is the circuit. T1 and T2 I have taken. So when T1 is conducting, you can see the blue arrow mark in which the current will flow through the load. Okay. When T2 is conducting, it is red arrow mark, right? So I can see when T1 is conducting, the current and voltage directions are different through the load. When T2 is conducting, the current and voltage directions are different through the load. It means what is happening is input I am giving DC. It is a straight line. It can be from a battery, right? Okay. So it is a straight line. What I am doing is I am cutting the input DC, okay, into equal parts. Equal parts I have cut here. You can see here, right? Tick mark into mark, tick mark into mark, tick mark, like that. So I keep only the tick mark, okay. Whereas the into marked portion I cut from the DC and I paste it down below 0. Okay. Into mark portions are placed below 0. Right. Due to this switching action, what is happening is I am getting a bidirectional output. From unidirectional input, I am getting bidirectional output. Okay. The converter which does this cutting and pasting is what shown on the left hand side. Right. So what and all you can note from this is, right? So the input voltage is 220 volt DC, right? The output voltage is also 220 volt AC. The output is AC, but it is 220 volt only. Either it is plus 220 or minus 220. Don't bother about that Vs by 2, Vs by 2 and all. That is just for this thing, right? Say for understanding you take, right? Input is 220 volt DC. 220 volt DC, one piece of cake is cut, right? And it is pasted in the negative off cycle, right? Okay. Like this, when you paste, you get bidirectional output. So bidirectional output means it is AC, right? Now you can see one thing, you can observe one thing from this basic inverter is that by converting DC to AC, you cannot get a voltage variation. Okay, you cannot get a voltage variation, right? Whereas if you can make the switching to happen quickly, right? When you make the switching to happen quickly, then you can get a variation in frequency. Okay, so a basic inverter is a fixed DC voltage to fixed AC voltage converter with 0 hertz frequency to any hertz frequency. You can fix the frequency to any hertz, right? 50 hertz you want, you can fix. Switching, only the switching, the speed at which the T1 and T2 operates, you have to control. That's all. When you control that speed of operation, what you get is you get more and more frequency. Is this clear? Anyone having doubt in this DC AC conversion? So next we go for DC DC conversion. Okay, DC DC conversion is also similar to DC AC conversion only. Here also the input is 220 volt DC. Here also we cut the waveform, right? Or else we can say chop the waveform, right? I am again putting a tick mark into mark, tick mark into mark alternatively, right? Tick mark portion alone I am keeping. Whereas instead of taking that into mark and pasting it down, I am discarding it. Okay, I am discarding this into marked portions. When I discard the into mark portion, only tick mark portion will remain in my output. Okay, when this is happening, you can see that input is 220 volt DC, that full, right? Due to the switching, what has happened is I am getting only 50% of the output. 50% of the input as output. So it means I will get an output of 110 volt DC, right? Through the chopping, right? So this is why this is called a chopper. And the converter which does this action is called the DC-DC converter or DC-DC chopper. You can see very simple circuit I am showing. Just since I am just working on the basics, okay, you can see a voltage source, that is a SCR and a load. You have to switch on that SCR, switch off the SCR. That's all. When you switch on, there will be output. If you switch off, there won't be output. Okay, right? So you can see the input area is more, whereas output area is less. So it means output area is only 50% of the input area. It means if input is 220 volt, output will be only 50% of the input, that is 110 volt DC. Okay, right? So with this NC power electronics part of what this lecture. Okay, is it clear? Anyone having any doubt in this? AC to DC converter. So here also you can see the waveform is changed. The shape of the input waveform is changed. Okay. Here also you can see the shape of the input waveform is changed. Okay. So here also you can see the shape of the input waveform is changed. Right. Okay. So this is not, the output is not pure DC. For getting pure DC, again we need filtering. Right. After you give this to filter, only you will get pure output in this case, as well as in this case, as well as in this case. Okay. All these three cases need filtering. Okay, or filters. The filters can be inbuilt within the converter itself, or we can use it separately. Clear? One of you open your mic and tell whether you have understood or not.
Yes, sir. Clear, sir.
Yeah. Thank you, Kalyan Kumar. Now we go to the next topic, power electronics in microgrid. How power electronics is required in microgrid. Okay. Right. Role of power electronics in grid stability. So what is stability of the power grid? I have seen that all the lectures from the beginning, from first day, right? Everyone states this, right? Grid stability. Okay. Right. So it is a repetition only again and again. Right. So power grid stability is the ability of the grid to return to normal state after experiencing a different disturbance, maintaining a balance between power supply and demand. Power electronics helps enhance grid stability in several ways. Right. We'll say what are the ways in next slide. Okay. So power grid stability is very, very important. Okay. If there is a power system engineer in this group, okay, if there is a power system engineer in this group, okay, kindly answer my question. Okay, if there is a grid failure, how much time it requires to bring the grid back to form? Power system engineer.
Sir, it depends upon the what kind of a fault it is, sir.
Normally, what is the minimum time that is
Minimum
required?
5 to 6 seconds backup would be there, sir.
No, I am saying about grid failure. When there is a grid failure,
hours to days.
okay,
Hours to days.
hours,
Several hours.
days,
Yes, sir.
hours, right? Okay, right. So minimum 2 hours it will require with isolation. Okay, minimum 2 hours requires with isolation. Okay, southern grade, if you take southern grade, it consists of Karnataka, Andhra, Kerala, and Tamil Nadu. Right? Let us say there is a huge power demand in Andhra, okay, AP. So what they are trying to do is they are trying to draw more power. Okay. When they draw more power, what happens is that due to heavy load, okay, the frequency will drop. Okay, when the frequency drop, all the machines will get slowed down. Okay, connected machines in the grid will get slowed down. Right. Suppose the frequency is dropping below a certain value, that is 3%, it seems 50 means below 47, right? If the frequency drops, right, one of the machine will pull out. Okay, somewhere, let us say thing is happening in what AP, but the Mettur power station, which is in Salem, right, that machine may pull out of synchronism. Okay, when that machine pulls out of synchronism, that machine will be lost. Already the load is heavy. When one machine is lost, it will be transferred to other machines. The next machine in the network will similarly, very quickly this happens. It is a cascading effect. Very quickly, the machine in Kerala may go off. Okay, next the machine in Krishnadasagar power generation plant, it may go off, right? So this cascading effect will pull down the entire grid, okay? And suddenly if you see, entire southern states won't be having power anywhere. Everything will come to standstill, okay? It means it is, we have to take immediate action, right? So what they will do now, they will island, right? They will island the few generations, okay, like those supplied to airports, railways, okay, those infrastructures, they will island, and they have to restart the entire plant again. That is the generator alternator, which has come to stop. Okay, it means it will take minimum of 2 hours to 3 hours to start the machine again, even if it is in islanded mode. To connect the entire grid back into action, it may take a lot of hours, as said by some power electronics engineer, right? Or even 1 day or 2 days also. Okay, right? So grid stability is very, very important. Nowadays, this is not happening. If it happens, okay, it is a okay big event in power systems, right? Okay, it will affect the entire nation actually. So frequency stability means, as I said, frequency is very important. Power electronic interfaces can aid in frequency regulation, right? For instance, during the periods of high demand, inverters can be controlled to feed additional power into the grid from the energy storage systems, helping to stabilize the frequency. So previously we didn't have energy storage systems, right? So old power engineers who have studied power systems way back 15 years, 20 years, they would have learned one term called a spinning reserve. Okay, spinning reserve only is a reserve which is used to face this high demand. Okay, nowadays it is not like that. We have energy storage system. Okay, even in our house we have, even in your house we can overcome power outage. How? We are having inverters, right? How your inverter works from the battery and supplies the power to your house during the power break. Okay, same way even the big power systems, right, have energy storage systems that will help frequency stability. Similarly, voltage stability. Power electronic devices can manage reactive power flow to maintain voltage levels within acceptable limits. Devices like static wire compensators, static synchronous compensators can provide and absorb reactive power as required, help to stabilize the voltage across the grid. Okay. Then role of power electronics in power quality. So power quality concerns the purity of electrical power in terms of voltage, amplitude, frequency, and waveform. The power electronics contribute to improving power quality. So power electronics has entered into power generation, transmission, distribution, even consumption. Okay. Many of you are not using stabilizers for refrigerators. Why you are not using stabilizers for refrigerators? Why you are not using stabilizers for televisions? Can anyone?
Inbuilt stabilizers are already there. There will be choppers. They are going to maintain a chopper inside the television.
Yeah, right. What is chopper? It is nothing but power electronics. Okay, so power electronic converters, that is SMPS, switched mode power supply, after it came right into picture, switched mode power supply, we shed the transformers inside the what televisions. The televisions became slim. Okay, now we are using switched mode power supplies. We are using inverters. Inverter AC you have seen, no? Inverters AC doesn't require what? Stabilizers. Stabilizers is one thing which every house used to have 20 years back. For a refrigerator there will be a stabilizer. Okay, for a air conditioner there will be a stabilizer. For a television there will be a stabilizer. In a house there will be 3 or 4 stabilizers. Okay, according to the number of equipments. Right. Today there is no stabilizer. Okay, we don't use stabilizers, right? Because of advancement in the power electronics. Power quality also is maintained, right? So what is power quality? Harmonic filtering, right? Power electronic devices, especially converters, can produce harmonics in the grid, leading to power quality issues. However, when equipped with appropriate control strategies, the same power electronic devices can filter these harmonics. Active filters, for example, can inject current into the grid that are out of phase with harmonic currents, effectively cancelling them out, right? This harmonic filtering, right, even though here we are saying it is a happening thing in the power systems, right? The use of power electronics, one of the drawback is production of harmonics. Okay, right? So conventional power system did not have issues with harmonics, right? Conventional power system had an issue of only reactive power and real power flow. Okay, right? Reactive power control, real power control is the only control, right, what you used to take care of in the conventional power systems which were previous days. After we introduced power electronics into power system, what has happened is this harmonic injection has become a big issue, right? We use power electronics as a boon for the power systems, right, for controlling frequency, other things. But in return, what it gives to the power system is harmonics. Okay, right? Harmonics is nothing but SPB is singing a song. Along with SPB, some 10 people also sing the same song at different pitch. What will happen to the song? The song will be what? What will happen to the song? You cannot hear that song. If 10 unknown people, just walkers on the road, if you call them and ask them to sing along with SPB one song, SPB is a fundamental. Okay. The fellows who are singing along with them are harmonics. Right. They will sing at their own pitch. They'll swing at their own frequency. Right. So ultimately, SPB song will be damaged. Okay. Right. That is the effect of harmonics in the power system. The main role player in harmonic generation is the power electronics. So power factor correction. Power electronic interfaces like inverters, rectifier can be controlled to deliver and absorb reactive power, maintaining a near unity power factor. This minimizes the reactive power flow in the grid, reducing power losses and improving the overall power quality. Then we have voltage regulation. Power electronic devices are very good in voltage regulation. Okay. Power electronic devices can quickly react to the voltage sags, surges, injecting and absorbing power as needed to correct these voltage disturbances. So in those days, old days, if the frequency is dropping, right, then in the power station, they will be increasing the steam input. Okay. If they increase the steam input has to go and hit the turbine. The turbine moment of inertia has to be overcome. And then the turbine has to rotate fast to overcome the reduction in the frequency. See how much time it will take. It is all mechanical. Okay. Hydraulics, right? Hydro systems, mechanical thing. Right, which were happening previously. Right now, power frequency correction is very easy. It will happen very quickly. Right. So conventional power systems had those type of problems. Similarly, voltage regulation also, we have to adjust the exciter in the alternator in the power station. Right, to increase the voltage. Right, we have to change the flux. Right. All these things now came into very quick control through the power electronic devices. This is particularly important in microgrids or areas with high penetration of renewable energy sources, which can exhibit significant voltage fluctuations. So renewable energy sources, wind energy, solar energy are all what? Okay. They are worst fellows, right? Okay. They are highly unreliable sources of power. Not like even you can believe a nuclear power plant. It will either work, not work, binary, right? This wind power station and the solar power station and all, we don't know when the generation will rise, when the generation will fall. It all doesn't depend upon us. It's all depend upon the nature. Okay. So power electronics in microgrids. Yeah, microgrid, it is a localized grouping of electricity sources and loads that can operate independently of traditional centralized grid. The core component that enables this functionality is the power electronic interface, which governs the power flow within the microgrid. Okay. So power converters, including inverters, rectifier, are essentially for functioning of a microgrid. They facilitate the conversion of DC power from solar panels and batteries into AC power that can be used by most household and commercial appliances. Conversely, they can convert AC power to DC for storage or direct use in the DC loads. So power electronics in distributed generation, they are used for power conditioning and conversion. Okay. And then maximum power point tracking, right? By using a proper converter and a control algorithm, right, we can get the maximum power from a solar PV, right, without having tracking. So in olden days, solar tracking was that they will fit a motor, right? So that motor will make the solar panel to see, just look at the sun and it will follow the path of the sun. That is now no more required. Okay, that is a complex process. Okay, nowadays we have MPPT. Right, you just put MPPT algorithm, right? The voltage and currents will be matched, right, to produce maximum power. Okay, that is called as maximum power point tracking. Then grid integration also is very easy. Okay, you would have done, if you are an electrical engineer, you would have done an experiment in the laboratory, if you have not performed experiment in this in the laboratory connecting alternator through the infinite grid, okay, then you have lost something, right, which is of importance, right? So connecting a alternator to a grid is called synchronization. Okay, that synchronization is now taking the name as integration, right? Connecting solar PV generation to the grid, selecting a wind generation to the grid, or connecting a hybrid generation to the grid is called integration. So that integration is very easily done by means of power electronics. You just need a controller on the power electronic circuit. It itself will check whether the voltages are same on this side and that side. If it is not same, it will rise one of the voltages and it will match and synchronize, right? It will match the frequency, it will match the voltage, it will match the phase, right? And these are the three things which is required for synchronization. All these things will be automatically done. Okay, it is not a cumbersome process anymore due to power electronics. Okay. In microgrids and distributed generation, power electronics serve as a critical link enabling efficient power conversion, control, and management. Technology ensures the system can safely, reliably, and efficiently generate distribute power, contributing to more resilient and sustainable power networks. Right. In the following section, we'll look at specific case studies highlighting the role of power electronics in modern smart grid implementation. Example is power electronics in wind energy system. Okay. Without power electronics, there is no wind energy conversion. Okay, you can see how we have wind energy generator, wind turbine is connected to grid, right? How many power electronic converters are there, you can see. Similarly, in a solar energy conversion also you can see PV system with panels. So you can see we need power electronic converters. Okay. And either we can use it as standalone mode or grid connected mode. Okay. For all this operation, we require power electronics. Then third one, power electronics in hybrid system. Hybrid system means combination of more than one renewable energy generation, including the conventional generation. Okay. So you can see PV panels, wind turbine, combined heat power engine, fuel cell. Okay, different power electronic converter are required. For example, PV panels. If we take PV panels, the input is DC. That is, the output of a PV panel is DC. Then we have to convert the DC, right? Okay, and we have to use it, right? So you need a DC-DC converter. When you take a wind, normally we use AC generators. So we will get a unregulated AC from the wind generation, which we have to regulate it. Similarly, combined heat power engine, right? Okay, then fuel cell. Fuel cell also generates DC, right? So it is all power electronically interfaced, right? Then we have a energy storage system also connected. Okay. Then we can operate all these things in standalone mode, or we can connect them with the grid. Okay. If we have excess power generation, right, then we can give it to the grid. Okay. If the generation is less, then we can take power from the grid. Okay. All these modes of operation is possible. Various possibilities are there. So now we go to the converter sections, right? The main topic of this session. So DC-DC converters is what you are seeing. So three converters I have given here. Buck converter, where the output voltage is less than the input voltage. Then we have boost converter, where there is output voltage greater than the input voltage. Then we have a buck boost converter, where you can have your output voltage, right, more or less than the input voltage. Okay, it is a DC-DC converter. In this configuration can be also called as a DC transformers. Okay, so DC transformers, buck converter is similar to step down transformer, boost converter is similar to step up transformer. Okay, So we don't have a step up, step down configuration in a transformer unless it is we can have a tap changing, right? So if we have a tap changing transformer, then we can have buck boost configuration also. So in DC-DC converters, we have non-isolated converters and isolated converters. Okay, non-isolated converters means where there is no isolation. Okay, so there are 5 main types of non-isolated converters. They are usually the converters what I have shown here: the buck boost converter, cuck converter, charge pump converters are some of the examples of non-isolated converters, right? Why it is called as non-isolated converters is the source, load are electrically connected. The source and load are electrically connected here. Okay, so these are called as non-isolated converters. If there is an electrical isolation between the source side and the load side, then those converters are called as isolated converters. Usually, this type of converters, high frequency transformer is used in between in applications where the output needs to be completely isolated from the input. Then an isolated converter is necessary. Some of these converters are half bridge, full bridge, fly back, fly forward, push pull, DC-DC converter. In that, only few things I am going to show you today. So I can see a boost DC-DC converter, right, which will step up the output voltage. So the stepping up of output voltage is due to the inductor that is connected along with the source, right? Whenever you operate that switch IGBT, right, there will be a closed path from V in, L and the IGBT. Okay, the output will be disconnected. Okay, during this operation, right? So you can see a MATLAB simulation circuit there. It is a very simple simulation circuit what I have given, right? So whenever the IGBT is turned on, the supply from the positive of V in will go through the inductor. The inductor will store energy in it, okay, which depends upon the size of the inductor, and then the current will flow through the IGBT and it will go back to the source. When the IGBT is turned off, it means there is a disruption in the inductor current. So you all know that whenever the inductor current is interrupted by some means, inductor will respond to this interruption by changing the polarity first. First, the inductor polarity will change. Okay, then it will start to discharge. Okay, when it discharges, it will discharge the current. When it discharges the current, there will be a voltage appearing across the inductor. That is called as VL. So VL will be L into di by dt. Okay, L into di by dt is VL. Okay, so you can see that there will be a voltage across the inductor. Okay, there will be a source. Suppose source is 12 volt. Let us say source is 12 volt. The voltage appearing across inductor is 3 volts. Okay, so this 12 volt and 3 volt, they will be in series. Okay, so this 12 volt plus 3 volt will become 15 volt. So the output, the voltage, if you measure the output, it will show 15, which is greater than V in. V in is only 12, whereas the V out is 15. Okay, in this way, since the output voltage is more than the input voltage, this converter is called as boost converter, and this boost converter operation is due to L. Okay, inductor. The more and more value you put, more and more the time you keep this IGBT on, right, that much output you will get. Okay, so you can see the standard DC boost converter parameters. Okay, V out is 400 volts, right, and switching frequency is 20 kilohertz. So the choppers, all choppers operate at high frequency only, right? Maximum inductor current is 250 amps, right? Inductor current triple is shown, but you see I have not shown the input output waveforms because I have already shown you, right? Choppers output. Okay, input
Yes,
output
sir.
waveforms.
Yeah.
Hello.
Sir, sorry for the disturbance.
Yeah, tell sir.
Here, how can we set the switching frequency? How can we choose that switching frequency value as 20 kilohertz?
Yeah. Switching frequency here, it is chosen based on the design, right? So device what you use, right? IGBT, right? If it is going to be a SCR, what you are going to put, I cannot switch on at 20 kilohertz. So it also depends upon the values of L, okay? The device what we use, okay? And the devices what is there in the circuit. Even the diode what we are using, right? All these things should be capable of handling this switching frequency of 20 kilohertz. So that has to be designed. Okay. When you go through the design of DC-DC boost converter, you will have the design values given. Okay. Right. So IGBT converter, IGBT is a high switching frequency device. So it can withstand 20 kilohertz. You cannot expect the same with SCR. Okay. SCR, we cannot use it here. Right. So similarly, inductor has to withstand this 20 kilohertz frequency, right? So inductor design needs how many coils we have to put, right? What is the thickness of the coil? All these things will be decided by the design only. We have to design it, sir, right?
That means, is there any mathematical relation was there, sir?
Yeah, there is a lot of mathematical relations, right? Since I am giving only insight here, I am not using any mathematical relations in this thing. Okay.
Okay.
Right. I am giving efficiency versus current, right? So you can see the efficiency versus current curve. What you observe from the efficiency versus current curve is that you can see the efficiency is high when the current is low. The efficiency drops down as the current increases. Okay, right? Why this happens is that as the current increases, the switching losses will increase, right? As the current increases, the switching losses will be increasing, and the losses, that is the current flowing through the, say, suppose IGBT is there, right? The current flowing through the IGBT will be having a resistance, right? Okay, so current and resistance will give a drop in the IGBT. Okay, that current, when you take it as a loss, it is I square R, okay, square of the current. So there will be inductor. Inductor is nothing but a coil, right? It will have a resistance. Okay, small resistance will be there. So the current flowing through the inductor, current flowing through the IGBT, right? Okay, on various components, right? They will increase as I square components. Okay, since they are increasing as I square into R, right? So as the current increases, since the loss is square of the current, the efficiency drops down. You can see that at high currents, the efficiency is low. So simulation of converters used in smart grids and microgrids. Simulation tube used this MATLAB. So you can here you can see interleaved 4-channel DC-DC converter. Interleaving means using multiple converters in parallel. Okay, you can see here I have used 4 converters: IGBT1, IGBT2, IGBT3, IGBT4, right? 4 legs we are using here. So interleaving in a DC-DC converter involves using multiple parallel converter channels, often 2 or more, that operate phase shifted clock signals. This means that each channel switches at a different time, effectively spreading out the current and reducing the stress on any signal single channel. Okay. So here you can see the same switching frequency we have maintained at 20 kilohertz. Output voltage what we require is 400. Okay, and you can see the efficiency curve. First it is dropping down, and then it is slightly improving. Okay, right? This is one of the what you call due to controller action. This has happened. Okay, right? So initially the efficiency is high because, as I said, losses will be more. Okay, as the current increases, the efficiency drops down initially, right? As I said, I square R losses. Okay, then you can see that the efficiency improves. Okay, right? Instead of going down, right, which has happened in previous thing, instead of going down, the efficiency improves because of interleaving action, right? So that is the advantage of using interleaved DC-DC converter. Okay, right? As the number of parallel converter channels add up, okay, this efficiency will slightly improve. Then we have full bridge DC-DC converter. Here you can see the full bridge DC-DC converter where there is a high frequency transformer in between. So it means output load side and the power source side are disconnected. They are not electrically connected. Okay, they are, you can say, electric circuit, magnetic coupling, electric circuit, like that. Okay, it is connected. So what we are doing here, we are taking the DC supply and we are converting it to a high frequency AC. Then using a IC frequency transformer, we are again converting it to DC by using of diode bridge rectifier. Okay, then we are giving it to the chopper circuit on the converter circuit on the right hand side to the load. Okay, here you can see the reverse of what we saw previously with interleaved converter and boost converter is happening. That is, efficiency is increasing as you increase the current. Okay, right? So this converter will be less efficient, okay, when the current is less. Okay, it will be efficient only when the current increases. This is what the experimental results also show. This is what simulation results also show. So comparative table, if you see between all the three converters what I have discussed here. Okay, so boost converter, interleaved converter, and bridge converter, we say, right? Efficiency at full load. Okay, interleaved channel is 95%. Okay, full bridge is 91%, very close to full interleaved. Whereas boost converter is 80%. Okay, on the volume and weight and all I have given here. Okay, when we go for electric vehicle applications, this volume and weight and all matters. Okay, so EMI I have given here. EMI is very low in case of full bridge. Electromagnetic interference is low in case of full bridge. Interleaved channel, there will be some electromagnetic interference. Okay, in DC boost, okay, there will be a 50-50, right? Okay, somewhat more. So as a summary, each converter topology has its own advantages and drawbacks. The DC-DC boost converter does not meet the criteria of electrical isolation, whereas full bridge DC-DC converter meets the electrical isolation. Okay, and it is also suitable for high power transmission. Okay, because switching voltage and current are not high, right? So we go to next AC-DC rectification. So as I said, AC-DC rectifiers you have already seen. So they are employed to convert AC power from the grid to the DC power for charging batteries or feeding loads. So this is the input signal of the rectifier. Okay, you can see a diode bridge rectifier in the place. It is a uncontrolled rectifier. Then there is a filter. So what is happening in the filter? What is happening is the bidirectional current and voltage is converted into unidirectional voltage. You can see that is output of the rectifier. Then we have LC filter. After the LC filter, you can see there is a Paka DC what is coming as an output. Okay. So ideal rectifiers is shown here. Okay, it is a bridge rectifier. You can see the waveforms, right? So single phase rectifier, you can see the waveform, and three phase rectifiers also you can see the waveform, right? So what is the difference is a three phase rectifier will require less what you call filter because the ripples are less, right? Ripple magnitude is less. Okay. Now why we go for uncontrolled rectifier is good power factor. Power factor will be good, harmonics will be less, reduced losses will be there. So wherever you don't need controlling action, that is I want to convert 220 volt AC to 220 volt DC means I go for uncontrolled rectifier. Unnecessarily, I will not go for a controlled rectifier. Okay, right? Just conversion of AC to DC means you go for uncontrolled rectifier. Suppose, right? If you want control, then you go for controlled rectifier. So practical rectifier is shown here. So a practical rectifier, you can see that it will consist of source inductance LA, right, and series resistance RA, right, with all the bridges what we have here, and there is a C1 here, R0 here. So ideal characteristics required is this one. Practically we obtain the waveform what I have shown there. Okay, why we need control rectifier is to control the output voltage one, but it has low efficiency. There is a low efficiency in an uncontrolled rectifier, and main advantage of control rectifier is bidirectional power flow is possible. That is, a control rectifier can be used as both inverter as well as rectifier. Okay, so in rectifiers, what are the latest rectifiers we use in power systems? Okay, for microgrid technologies is active front end rectifiers are called as AFE. So they are 3-phase passive rectifier, 3-phase 2-level 6-switch boost type rectifier, 3-phase 3-level neutral point clamped converter, 3-phase 3-level T-type converter are the active front end rectifiers what we normally started using. So this is a 3-phase 2-level 6 switch boost type rectifier. You can see 6 switches are there. Okay, L1, L2, L3, right, are the source inductances. So on the right hand side you can see the current. Okay, due to this simulation, right, in ampere, and the voltage you can see the voltage actually the blue color portion is a pulse. It is shown in the box, right? This type of pulses is applied, so that pulses is appearing as the what you call positive and negative off cycle, but the average line to line voltage is shown as red color portion is the average line current, which is sinusoidal. Okay, and when you come to the DC link voltage, right, that is DC link voltage, you can see there is a high ripples in the output. Okay, so it change there is a ripple content that is after 695 probably from 695 to 705, right, there is a ripple voltage, okay, which is shown, right? So this is a 3-phase 2-level 6-switch boost type rectifier. Here how the boosting operation happens is due to the presence of this L1, L2, L3, right, like what we have seen in our boost converter. Here also the source inductance, right, plus adds on with the additional inductance what we are providing, right, in the input side, that contributes to the improved, right, increased output voltage. Then we come to 3-phase 3-level neutral point clamped converter. Okay, so here neutral point clamping is happening. Why we go for neutral point clamping is that the dynamic losses are significantly reduced when you go for neutral point clamped converter. So by clamping the neutral point, suppose the devices require a rating of 1200 volts. Okay, right, suppose the devices require 1200 volts each switch. Okay, by going for neutral point clamping, we can use switches of 600 volt itself. Off, the rating will reduce by 50%. Okay, right, because the switches won't be subjected to that voltage stress of 1200. Okay, it will get limited within 600, so that we can go for a reduced voltage rating. So if you go for reduced voltage rating, what is going to happen is that faster switching action will happen, right, and the converter will become ultra fast. One thing. Second thing is reduced rating means reduced cost and size of the converter is what we obtain. Similarly, the output ripple will be also reduced. Okay. So you can see that is evident from the waveforms. You can see, you can compare the ripple, okay, in the previous converter and this converter. You can see the ripple in the output has reduced. Okay, it is almost becoming that DC link voltage. That ripple is reduced. Okay, then we go for three-phase, three-level T-type converter. Right. So in a T-type converter, the output of a neutral point clamped converter and output of a three-phase T-level converter, what has been observed in the simulation is very same, right? But it can be found. I am not showing those things, right? The parameters. Actually, I should have shown that parameters, right? THD is less, right? Total harmonic distortion compared to neutral point clamped converter is less when compared to in T-type converters it is less when compared to the neutral point clamped converter. Okay, then neutral point clamped converter has had more switching loss, whereas T-type converter had less switching loss and higher efficiency. The efficiency was about 1% more, 1.5% more. Okay, in T-type converter compared to neutral point clamped converter, but the output characteristics and all will be same. The current, voltage, and the voltage, what you call the ripple contents, right? Magnitude of the ripple content, everything will be same. Only thing is we get low THD, low switching loss, higher efficiency. Okay, so when you compare these three technologies, right, at different frequencies. You can see the blue color indicates 2 level. Then neutral point clamp is given by pink, and you can see the T-type converter in the top. Right? You can see the T-type converter proves to be more efficient when compared to the other two-type converter. Right? When compared with the NPC, neutral point clamp, the efficiency of what you call T-type is closer to NPC for the reasons what I have told. Okay. Otherwise, the T-type and NPC are almost same only in input output this thing, except for the hidden things, that is total harmonic distortion, reduced losses. All these things contribute to improved efficiency, right? When the switching frequency is increased. Okay. How to control the EFE converters, right? So to control the active front-end converters, we can use linear controller, non-linear controller, robust controller, predictive controller, and intelligent controllers. So I can see the linear control means, right? PAID controllers are very, very easily usable controllers, right? There is another controller called proportional resonant controllers. The linear quadratic Gaussian LQG control is also used for AFE controllers, right? So in proportional integral derivative controllers, we can go for voltage oriented control. Okay. So this and all I am not explaining due to time constraint. Okay, this PPT will be available in the group. Okay, you can go and see, right, what these controllers will give. What will be the outcome of these controllers? Later you can study and get the insights. So controller normally preferred is due to reference frame. For all the three, this is a common controller. Okay, DQ reference frame, P, PI or PID controller. Okay, so here you can see real power and reactive power P and Q are given. Then KP, KD and all calculated. That is values of PI controllers constants. Then converting DQ to ABC and again ABC to DQ. Three-phase, three-level rectifier. That is what we have seen, right? Previously active front end. So for all the three active front-end rectifiers, we can use this common controller. So when we go to non-linear control, okay, when you go for non-linear control, sliding mode control is there for more than 20 years. All of you know. Partial feedback controllers, hysteresis control is there. So hysteresis control, we can use current control or direct power control. Okay, in the hysteresis control. Right? Then we have a robust controller called as H infinity and mu controller. Okay, what is this H infinity controller? It is a type of robust control algorithm that aims to achieve optimal performance in the presence of uncertainties, disturbances, and modeling errors. Okay, so all type of uncertainties will be considered. Disturbances will be there, right? Modeling errors, all these things will not affect the H infinity controller. Okay, it is a part of robust control theory. If you have studied control system, there is a thing called as robust control theory, which focuses on creating control that can maintain system performance despite variation in imperfections. Okay, even if there are imperfections, the controller will behave right efficiently. Okay, right? That type of controller is called a robust controller, and one type of robust controller is H infinity. Similarly, we have mu synthesis. Okay, so mu synthesis also works under the same principle only. So in control system, uncertainties refer to the unknowns or variations in the system parameters, external disturbances, or modeling errors. Okay, you can say there will be some structured uncertainties. Okay, structured uncertainties means these uncertainties can be described using a specific mathematical model. Okay, that characterizes the structure and nature of this variation. The mu synthesis is especially effective in the systems where uncertainties is not random but follow a structure. So in H infinity, even it will take care of even random uncertainties, whereas in mu synthesis, right, when the uncertainties are structured, okay, such as parametric variation, sensor noise, or external disturbances, all these things, right, the mu synthesis will take care. So these robust controllers or latest type of controllers, what you can use it, okay, right? So as a PhD guide and as a PhD evaluator, I see still the people are using PID controller, sliding mode control. Only conventional control they are using always, right? You have to try with the new control algorithm, okay, and go for the controllers. Then we have predictive controllers. Hope you know what is predictive control. So in that deadbeat predictive controller, hysteresis based predictive controller, trajectory, model predictive control, then finite set of MPC, model predictive control, okay, then continuous control set of MPC, right? So this you know, right? It will result in optimal switching sequence. MPC is one of the final control set. Then optimal switching vector MPC is another control, right? All these controls I am never seeing in many of the PhD work that is presented. All are going for normal control algorithm. You are using whale algorithm. You are using ant colony. That's all these things I am saying. But when it comes to the controllers, okay, people are not right. They are very choosy. Then we have intelligent controllers. Intelligent controllers, repetitive neural network, fuzzy logic, and autonomous controllers. When we go to DC AC inversion, there's another 3 minutes. Okay. So you know how the inverter works. So normally what we use in the power systems is multi-level inverters. Multi-level inverters can be classified into single DC source or multiple DC source. Single DC source means NPC, neutral point clamped, then flying capacitor. So in neutral point clamp, you can see active neutral point clamp, T-type, NNPC. Then we have a cascaded H bridge. Okay. Then we have a modular multi-level. Then we have ST, right? ST, CT, HT type, right? HT type means H bridge trinary, okay, cascaded trinary. Then we have symmetrical trinary, or some of the classification of the multi-level inverters. So this is a 3-level NPC MLI, okay, what we use to convert solar input into AC output, okay. Wherever DC DC source is available, or a battery voltage DC source is available, or a fuel cell output, okay, from this you have to convert the DC to AC. Then we can use this 3-level NPC MLI. Then we have 3-level 3-phase active neutral point clamped multi-level inverter. So here again you can see here it is active neutral point clamped multi-level inverter. Conventional NPC has a limitation of the DC bus voltage, right? To overcome this difficulty, APNC MLA is used, right? Okay, which has a clamping diodes that are replaced with the control switches. This is what ANPC. Then 3-phase 3-level T-type MLA is there. This is also used, okay, for conversion of DC power to AC. That is 3-phase 3-level T-type MLI. Then we have 3-phase 3-level N-square PC MLI, okay, nested neural point clamped MLI, right? Yeah, N-square PC MLI topology is derived from the combination of flying capacitor with an neutral point clamp in multi-level inverter configuration, which offers 4 levels of output voltage. The 4-level N-square PC configuration has lower diode count than 4-level NPC converter itself, and it has a lower capacitor count than 4-level FC inverter. That is the advantage, the difference between the normal NPC and NNPC. Then we have a 3-phase 3-level flying capacitor MLI. So the modulation techniques what are used for MLI is shown here. Okay, multi-level control modulation techniques, space vector modulation, voltage level based algorithm, 2D algorithm, 3D algorithm, hybrid modulation techniques, selective harmonic elimination, multi-carrier PWM, nearest level this thing, place shifted PWM, double shifted PWM, PD, POD, APOD, PWM are there. All modulation techniques. These are all waiting for you people to use them and do research. Okay, so this is a comparative statement, okay, between the various type of converters, right, and topologies, right, advantages and drawbacks. I will you read from this comparison from this slide what I will give. Similarly, these are the merits and drawbacks of control techniques: scalar control, vector control, predictive control, and sensor control. Right? What are the advantages and drawbacks? Right. So these are the 2 references what I have referred. These are publications. Right. We can go for questions because 9:30 it is 7:30. Right. We have to close this session to enable next session to start. Okay. People having questions can ask. Any questions?
Hello, sir. Good evening, sir. I'm Ilango, sir.
Yeah,
hello, sir.
Yeah, tell sir.
Sir, now only I have started my research in energy management, harmonic compensation of DC microgrid using decentralized control architecture.
Yeah.
So further, if I want to contact you regarding your thing, if you have any email or any further programs, how can I contact you, sir, regarding this?
Yeah, it will be right. You can contact the coordinators, right? Okay, or you go to JAIN University website and see there. My contacts will be available.
Okay, sir. Okay, sir. Okay, sir.
Right?
Thank you, sir.
I'm mainly working in my microgrid technologies only.
Okay,
right?
sir.
So
okay, sir.
Yeah. So see, microgrid. See, one problem with microgrid is right. If you have a solar grid.
Okay, sir.
Okay, Ilango sir. Solar grid,
sir.
you are producing DC.
Okay, sir.
Okay, the production is DC. Right?
Yes, sir. Yes, yes
okay.
sir.
Right. It has to be connected to the load. Right.
Yes, sir. Yes,
okay.
sir. Yes.
So you know reactive power.
Yes, sir.
Right? If you need water from one place to another place,
Yes, sir.
you need a bucket to carry that water.
Yes, sir. Yes, sir. Yes, sir. Then only it can move. Yes, sir.
Yeah,
Yes,
then
sir.
only the water will move from there to here. The bucket is nothing but reactive power. Without reactive power, real power cannot flow.
Oh,
Right?
okay, sir. Okay, sir.
Correct.
Okay, sir.
So if it is a solar panel installation and there is a power generation there and the load
Okay.
has to be supplied,
Okay, sir.
okay, and the load is going to be AC load, which is
Okay,
going
sir.
to have a inductor, how
Okay,
will
sir.
you do the compensation? How will you generate the reactive power in that setup? Have you ever thought of this?
Oh, I didn't thought so.
Yeah, it means
Yes, sir.
there will be a, suppose there is a motor in that load. The motor
Okay, sir.
requires reactive power, but the solar panel will not give what? Reactive power.
It will not generate, sir. Actually,
It will not
it will not.
generate. So
Yes,
who
sir.
will
Yes.
generate the reactive power for that motor? In a power systems, there will be capacitors somewhere, synchronous somewhere, right?
Yes, sir.
Okay,
Yes, sir. Yes, yes, sir.
right. Okay, this and all, like I have not gone into DC microgrid and AC microgrid. Okay, DC
Okay.
microgrid has separate part. We don't have that much time to discuss about DC microgrid and AC microgrid. I have just
Okay.
shown about microgrid and converters what is used, more concentrating on power electronics. There are a lot
Sir.
of concepts what you have to study, sir,
Okay, sir.
on the microgrid. Okay,
Okay.
then
Okay,
only
sir.
you can enhance your PhD. Right?
Okay, sir. Okay, sir. Sir, you are conducting some more other programs also, sir, through this ATAL or some.
No. We every day going to college and managing the regular activity itself. We have a lot of time. But whenever we are conducting programs, we will inform. Sir.
Okay, sir. Okay, sir. Okay, sir. Thank you. Really, really, your session is very much insightful and it gives me more knowledge, sir. And right now only I'm starting. It gives very basic ideas also. Very
So
super.
for those people who don't know power electronics, I have to teach them power electronics. Then only I can come to the converters. For that only I have like that.
Yeah, really very much useful, sir. Thank you so much, sir.
Thank you, Mr. Lembu. Right.
Thank you, sir. Thanks, sir.
Any more inputs? Kishore sir, shall we close the session? Madam, Shweta madam.
Shweta madam, are you there? Yeah, sir, you can stop your sharing, sir.
Okay, sir.
Yeah, meanwhile, I will call the Shweta madam. Yeah, dear participants, please open your video. We will go ahead with the photo. I request all the participants to open your videos, please. We have around 196 participants and around 150 participants are joining, so it will take a bit time. So please kindly open your videos and okay. Thank you, dear participants. Thank you so much. And we will just, sir, Ellison, sir, you have given very great insights. In this context, I like to express my great words about the research in Jain University. Actually, as a research coordinator, it's I feel it's my duty to inform all of you. Today is 11th, yeah. Today is the last date for the research program in JAIN University, so you can apply. We have already shared the links and everything also. I will share once again also. And see, we have very much potential faculty here. Even if you join under me, there is no problem. You can take guidance from Eliason sir also. If you join any of us, you can take guidance from the, it's like a university and it's a department. So we have really potential people with us, and even some new faculty members are also joining our team as they are just completing their PhD and they are ready to continue their work. So I request every one of you, please utilize this opportunity from our Department of Electrical and Electronics Engineering, JAIN Limitable University. And all the participants are asking only one question, such that kindly give your email IDs. Participants, you no need to worry. This is a part and parcel of the program. I will definitely share all the email IDs and phone numbers of each and every resource person to you. Okay, I have already taken from the portal. Every data is available with us, so you no need to worry. I will definitely share it with you. This is the only way we can connect with the people. So this is the main purpose of this FDP. So you no need to worry. I will definitely share it with you. And Sweta, madam.
Yes, sir.
Yes, madam. Please give your note on Eliason sir's lecture, and we can start with the next speaker, madam.
Yes, sir. Yes. Thank you so much, sir. Your session was very helpful to us, because I personally didn't know the idea of power electronics. So thank you so much for that, sir. And participants, kindly check in the chat box. I've shared the feedback link. So please do fill the feedbacks. Sir, Kishore, sir?
Yes, madam.
Maybe we have to give to Hanama.
Yeah, Hanna madam is here.
Yes.
Yeah.
Ma'am, thank you. Ma'am, thank you. Right, I'll sign off. Right, thank you.
Yeah,
Thank you so much, sir. Thank you so much.
Thank you all. I would like to introduce our speaker for the next session, Dr. Suresh Maganti. Dr. Suresh Maganti is a member of IEEE, has completed his bachelor's degree in electrical and electronics engineering from CR Reddy College of Engineering, Eluru, India in 2011. He obtained his MTech degree in Power System Control and Automation from Gayatri Vidya Parishad College of Engineering, Visakhapatnam, Andhra Pradesh, in the year 2014. In 2023, he earned his PhD degree in electrical engineering from the reputed institution IIT Roorkee, India. He served as an assistant professor in Vignan Institute of Information Technology, Visakhapatnam, India from 2015 to 18. Subsequently, he worked as a senior research fellow on the India-UK collaborative project, Zero Peak Energy Building Design for India, an initiative under Net Zero at IIT Roorkee from 2018 to 2023. Following this, he worked as a senior research level at level number 2 at the Dubai Electricity and Water Authority R&D Center for Business Development and Excellence. He is currently the senior manager for Smart PV and Battery Energy Storage System Product Middle East and Central Asia at Huawei Digital Power, Dubai, UAE. His research interests include design and controlling of grid-tied converters, AC to DC, DC to DC, DC to AC controllers, control and protection of HVDC systems, modular multi-level converters at medium and high voltage range applications, weak AC grid interactive HVDC systems, STATCOM, PV and battery energy storage systems, battery management systems, microgrids, and smart grids. We welcome you, sir, for this fruitful session. We are expecting more information from you, sir. Over to you, sir. Thank you.
Thank you, Hannah. Thank you for introducing me. And also, I thank.
Excuse me, Suresh, sir. Yeah, yes. I want to tell something about you, sir. Yeah, Suresh, sir is my colleague in my previous institute. So now all of my colleagues at Jain University can come to know why I keep on telling and discussing about my previous institute. Because my previous institute is one of the great institution and where great colleagues are there. So many are from NITs and IITs, and he is one of our beloved colleague in Vignan Institute of Information Technology, and he finished his PhD from where I was finished my PhD. So I feel very happy that he has gone to that level, collaborating with the international projects and collaborating with the international government electricity organizations. And I feel very happy, sir, Suresh sir, and we are really blessed that today you are taking this session for us. Thank you so much, sir, and please continue your session, sir. Thank you. Thank you so much.
Thank you, Kishore sir. It's bit over. Okay. Let's first of all, I thank Jain University team for giving me this opportunity. So let me share my screen. Yes, are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, thank you. First of all, I thank Jain University Electrical Department team and Kishore sir. Thank you for giving me this opportunity. So, so today I want to talk about some high-level slides. I want to make you tour about the world's largest microgrid as well. So I want to talk about what the real industry standards and industry practices I want to make you experience today. So the main topic is advancements in battery energy storage system for grid integration, and it's what are the standards and what are the challenges when we go for grid integration, what are the key features that we required. So let's dive into the slides. So let's coming to the contents. First, I would like to give a brief overview about my company and what is digital power and its overview, and then we will talk about battery energy storage introduction, why we are going for battery energy storage systems instead of many alternate energy storage systems are available, and also we'll talk about grid level applications. After that, what are the challenges when we integrate with the grid, especially at the grid level challenges, and what are the trends really that motivates towards the battery energy storage systems and its installations in the grid. And then we'll discuss about the battery energy storage solutions. Mostly here I will talk about some Huawei solutions as well as in comparison with industry standard solutions, and also its key features, how the battery energy storage system will possess different key features. In the previous lectures, we heard many grid stability, frequency regulation, voltage regulation. So how it goes in reality and how it will be. So let's see all those slides. And also how the Huawei will build advanced BSS. So its design techniques, its design way, and the way of validation and going into on-field, and what are the successful installed projects all over the globe. And also we will have a virtual tour of the projects as well. So let's go into the slides. So Huawei is a technology giant and it's a telecom giant. It has its presence over 170 plus countries and all the regions. It has almost 200k employees working in Huawei, around more than 55% of employees working in R&D, and which ranks global number 5 in global R&D investment, and also which holds largest patent portfolios, which is around 140,000 patents. And its actually mission is bringing digital to every person, home, and organization for fully connected and intelligent world. This is the mission always drives Huawei being a technology leader, and it has its own chip manufacturing as well as its own operating systems for mobiles as well as the laptops, and it is providing cloud services, and also it has various other subsidiary companies as well. So I belong to digital power, so I more talk about the digital power division. There are many other divisions as well. So when it comes to digital power, it also has wide presence over 170 countries and many regions. Over 10,000 plus employees are working in that. More than 60% employees are working towards R&D research and development. It has 12 R&D centers, including Middle East, and across the globe. You can see the mostly the product development R&Ds at the Shanghai. So and it's I'm getting echo. Yeah. So it has a lot of R&D investment towards the product development. So am I missing something?
Suresh sir, sorry for interruption.
Yes.
And that is audio level is a little bit poor, sir.
Okay. Let me look at that.
Sorry, sir. You can continue now.
Yes.
We are sorry, sir. You
So,
can continue now.
yeah. So coming to digital power, it has active 2122 active patents. So now from the digital power, it has dispatched the inverters which counts the in 2023 145 gigawatt. So which is the number one inverter which has sold in more sold inverter around the globe, and the total installed capacities that done by the Huawei is 445 gigawatt PV. And when it comes to energy storage system installations, so it is accounts to 20.5 gigawatt hours all over the globe. So I'm mostly belongs to Middle East and Central region. So in this region, so you can see the digital power installations. So it has total installations of 9 gigawatt plus PV delivered, which is already commissioned and it's working without any issues. And 1.3 gigawatt hour energy storage has been delivered. So it is under working. And also it has very big business with the data centers, which has total installation capacity of 1500 megawatts plus. So apart from the digital power businesses, it has its presence in enterprise, that is mobiles manufacturing, and various laptops manufacturing, and its own chip manufacturing. And it has its own applications, and it is providing power service to various partners. And also the digital power mostly working with Middle East partners like Masdar, Aqua, and Aramco. So this is the small brief about the my company. Let's dive into our slides. So let's talk about the BS introduction. When we talk about battery energy storage system, we know we have many energy storage that exist, such as mechanical, that might be pumped hydro energy storage. There is a kinetic energy that's stored in flywheels. So these are all a kind of energy storage. So another type of energy storage, electrochemical energy storage. That's all mostly batteries will come. So some electrical storage, we know the capacitor, so it will store energy and it will give some whenever we need. So it depends on the conditions. And also chemical energy storage, that is hydrogen fuels, hydrogen works with the fuel cells. So in these energy storages, it has different characteristics, and it will be used for different purposes. For example, pumped hydro storage will be used when the peak power comes into the picture, peak power, peak demand. So mostly people will use it as a peak modifying generation. When the flywheel comes, when the system is under frequency regulation, or is there any huge demand that occurs, the flywheel, the energy stored in the flywheel will comes into the picture to cater the frequency requirements, to stop the frequency ROC curve. So these are the energy storage that are available. Let's see what are its purposes and what are its characteristics. So when we see the grid level things, so the picture you are seeing is, so this is the power requirement level. So this is 10 megawatt, this is 100 megawatt, then 1 gigawatt and 10 gigawatt. Sorry for this mistake. So when you talk about the grid level applications, that is voltage regulation and frequency regulation, what are the energy storages will be feasible to use for this application? For example, if you see the supercapacitor and flywheels, so mostly it can feasible to participate in frequency regulation, especially in primary frequency regulation. So it won't provide longer term energy support. So if we talk about batteries, so it can support generation support as well, and storage we can. So these kind of, so if you observe all the applications, the batteries have wide range of characteristics. It can support many of the applications. So this is always pushing the batteries for various for the grid level energy storage systems. And also the battery has response time from seconds to a day. So we can use battery storage. It can respond within seconds, and we can use it, make use it of hours and day also as a support, generation support or different kind of grid level applications. So let's see what are the, so here we will come to know that batteries are much more better when it compared with other energy storages. So let's see which battery is better, because we have many battery technologies. So we have lithium-ion batteries, sodium sulfur batteries, redox flow batteries, and nickel cadmium batteries, and lead acid batteries. We know lead acid batteries we all see in cars or vehicles. That's the batteries, those kind of batteries. So among these technologies, they will have different type of characteristics. That is, if you see the energy density of lead acid battery, so it will give 30 to 50 watt hour per kg volume. So if you see the lithium ion batteries that we will use in mobiles or grid level application, car and everything, so it will give 150 to 250 watt hour per kg. So that means very less, it will occupy very less space. And also most of the industries will concern about the efficiency as well as the economics of the any product or anything. So the round trip efficiency, round trip means charging plus discharging. So combined cycle will be a round trip efficiency. So if you see the lithium ion batteries, it will accounts 95% it will give, which is far better than other battery and storage technologies. If you observe the lifespan, so it will it is also have better life. But if you compare with eco-friendly, so when compared with other technologies, it has very good eco-friendliness. But on fully environmental basis, so it is not still validated. So there are many challenges when we talk about the environment. So there is still challenges when we say about the eco-friendliness. So but when compared with sodium sulfur and redox batteries and lead acid batteries, yeah, still lithium ion battery has upper hand in eco-friendliness. And also we should thank recycling technologies, so that it is reducing the risk of the batteries towards its environment. So you can see full details whatever the source that I have mentioned. So let's see what are the components in the battery and storage system. So when we say battery and storage system that is connected to the grid, so there are some typical components will be there. So that is a cell, then it will be formed a module, that is the cells connected in series and parallel. Then these modules will form a pack. Then these packs will form a rack, and then these racks will be arranged in any container or a building. So that will comes a battery energy system of maybe in container maybe 20 feet or 40 feet. So these battery system will be managed by the battery management system. So in this battery management system, we'll have battery thermal management system, which will monitor each and every cell, pack and rack and its temperature, and also it will maintain. So if it detects any abnormalities in the system, so it will generate alarms or alerts to respond very quickly, or sometimes it will take the decision based on A and ML that the algorithm that has been embedded. It will take the decision and it will make the battery system secure. So this battery system will be connected to a power conversion system that might be having two stage or one stage. The two stage is DC DC, and then DC to AC will be connected to the grid. So single stage means direct DC to AC. So this the converter power conversion system will be driven by the energy management system. So who will instruct energy management system? It is mostly connected with the distribution system operator or transmission system operator. So it will receive the signals, or depends on the local that may be voltage and frequency sense. It will act accordingly. Sometimes it will prioritize the signals that comes from the energy that comes from the TSO and DSO. So accordingly, it will decide the discharge and charging of power conversion system based on the battery system availability. So let's go into further details. So when we talk about the grid level applications of the battery energy storage system, there are a lot of applications. Some applications really require the battery energy storage system. Some applications really don't require the battery energy storage system. But if the battery energy storage system is installed in the system, so we can utilize it for other purposes, other applications. For example, energy. For example, power quality services. If the battery, no one really prefer battery energy storage to do power quality. So if the battery is already installed in the system, so we can take it as an advantage so that we can use it for power quality services as well. So let's discuss grid level applications one by one. So first one is electric energy time shift. So sometimes right now the conventional grids are mostly flooded with solar or wind, so which is intermittent in nature. So sometimes the energy is more, the penetration is more than the demand. So at that time, so we can use the battery energy storage to store the some amount of energy, and we can use at the peak levels, because the tariff will be different from off peak to peak level. So those latter use, that means energy shift, we can use a battery energy storage. So the range of its battery energy storage may be 1 to 500 megawatt, and it requires 1 hour, sometimes maybe a discharging of 5 hours. It depends on the design. So it accounts of around 250 plus cycles per an year. The cycle means one charging and one discharging. So the next application is electric supply capacity. So when we talk about electric supply capacity, for example, the generated energy is very much high. So and the demand is very less. So that time we will use. If the capacity is very less and the demand is very high, so sometimes from off peak to on peak, we can shift these kind of capacities we can avoid by using the energy storage systems. And next one is regulation. So regulation comes under ancillary services, that might be voltage support, unbalance compensation. These ancillary supports can be done by using battery energy storage system, but for only just for doing unbalanced compensation, it's not much recommendable to install the battery energy storage system. If it is installed, yes, it can be use it for unbalanced compensation, but towards distribution network facilities to regulate the voltage support as well as the network support, battery energy storage is much required. It will give them other support as well. So like a black start or maybe network support. If it is a vast voltage profile, it can improve through active power injection. So such kind of things, it's really required. So another one is the spinning battery and storage system will maintain spinning and non-spinning and supplemental reserves. So in conventional grid, we know we have for some synchronous generators will be standby for using as a spinning reserve whenever any frequency events or sudden loss of any generation comes, or sudden increase in the load that comes. So in that situations, yes, a battery and storage system can be used as a spinning reserve. It can respond very fastly. So from within seconds to an hour. Another important grid application is we can defer the transmission upgrade and distribution upgrade. Sometimes we need to construct a new transmission lines, new distribution lines, depending on the demand. So that time, while by installing battery energy storage system, we can delay the installation of transmission lines, or we can permanently avoid the installations. So those kind of grid upgrades, so we can
Yeah.
take the support of battery energy storage system as well. Yes. Yeah. So previously I talked about the voltage support. Yeah, we using battery energy storage system. Yes, we can use it for voltage support as well. So another important application of battery energy storage system is black star. So which is very much currently demanding right now. So, and the next one application is load following or ramping up of renewables. This is one of the important applications. Sometimes if the solar penetration is very huge, so if you see in the morning, the solar is ramping up at a rate, maybe 50 megawatt per hour, maybe 100 megawatt per hour. So it's ramping up. So it doesn't mean that demand should ramp up at the same rate. So at that time, to make a balance between ramping up power generation as well as the demand, so energy storage will be the better option. So the balance between ramping up generation as well as the demand can be maintained very smoothly. And also battery energy storage is much better useful, especially to relieve the congestion of the transmission lines. So the storage system size may be it vary from 10 to 200 or 300 megawatt hours, and it requires 1 to 4 hours discharge to relieve the congestion of the transmission lines. So the another thing is to maintain the power quality. So if the battery energy storage systems are installed in the system, yes, we use it for the maintain the power quality. So that it can participate harmonic compensation, sometimes interruptions it will, and also it can use it for the power factor improvement by injecting the reactive power into the system. If it is a distribution system, it can inject active power into the system and to provide network support. So these are the important and typical grid applications where the battery energy storage system is really useful. So let's see what are the challenges that we will face when we use a battery energy storage system for the grid integration. So the most important challenge is when we say battery energy storage. So the safety challenge is most important, because we all mostly experience it with the hazards of that we saw on electric vehicles. So it may catch fire, sometimes it may explode. So the security safety challenge is very much important. So when we say the battery VS energy battery energy storage system safety, there are risk sources. So that may comes from internal or external. So the risk sources are non-battery risk, that may because of short circuit internally, or maybe some external external thing can initiate short circuit internally. So these are the non-battery risks. Some external risk that might be is if you while commissioning, the battery container may fall from 2 meter height or 1 meter height. So the sudden fall, the stress on the battery cells or the battery packs may damage the battery cells as well. And also the vibrations, maybe earthquakes, that may damage the batteries sometimes. So damage the battery inside the structures that we previously talked about, the containers. So, and also sometimes the atmosphere, so the condensation, that is humid atmosphere, may leads to precipitation on different layers of the may enter into the containers and leads to different precipitation. So we need to contain the air also, so to avoid these precipitation or condensation kind of things. And another risk source is insulation failures or over voltage and over current. These may mostly come from the grid side. So another risk source is manufacturing defects, that is properly not properly having lithium plating, these kind of internal defects. And one more important thing is a failure of battery management system. If any fault occurs, or any communication issues or sampling issues with the battery management system, that leads to a failure. So if any risk initiates, so this will be the failure path of the battery energy storage system. First, it will increase the rapid rise temperature inside the cell, then it will leads into thermal runaway, then it will catches the fire, then it will increase the temperatures of side by the cells, then it will further it's like a kind of leads to an explosion, since it is a condenser. So if you don't take any proper measures to dispose these temperatures to outside environments, it leads to an explosion. So there are some use case and there are some experiences, that is the global experiences that faced these battery energy storage system failures. So this is the one of the failure that has a region that has occurred in California in USA. So the main source initiation is the rainwater enter into battery and storage system and leads to a fire catching and leads to a fire in the battery and storage system. So around 2 million loss in this situation. And similar kind of problem in Australia. So the external water flows into the busbar and busbar copper bar into the system and leads to a damage in the battery and storage system. So and another thing is this is towards internal part. So during the manufacturing, the cells has not been tested properly, so it has caused mismatch between cells and ultimately leads to a thermal runaway. So these are the experiences and use cases that has been hazards that has been seen in 2023 across the globe, various regions. So and also another challenge is so till now we talk about what are the safety challenges that are there with battery and storage system. So another challenge is revenue challenge. So how we once we install the battery and storage system, how to get the revenue. So how to yield the revenue fully. So based on the investment, how to get the return on investment. So in this, the mostly challenges when we say battery and storage system in the market. So the main dominated solutions are central solution as well as the string solution. So Huawei mostly manufacture the string solution. So when we compare with industry centralized solution, so the availability is less than string solution, that is about 98% availability. That is so it will reduce the revenue gains of the system. And sometimes because of not properly maintaining the battery charge and discharge, not proper battery management system, so we can't discharge entire battery management system up to 0, or we can't charge the battery up to 1000. So I will explain why it will happen. So that time, so that may limits the available capacity of the battery and storage system. That may leads to revenue losses as well. Sometimes because of the poor maintenance and worse maintenance, so it requires, so that may see the immediate discharge of the battery. So we know, we all experience with our mobiles. So after usage of maybe not properly maintained, if you don't properly maintain the mobile charging, after 1 or 2 years, if you do it a full charge, it will discharge in within half an hour. So those kind of scenarios also will come. So it will affect the life cycle. So this is also one of the revenue challenge that will degrade the that will reduce the revenue comes from the battery and storage system. And another one is in the traditional, mostly battery packs and racks, the SOC is calibrated, and so the packs will be balanced based on the manual kind of. This requires a lot of maintenance. So this also consumes a lot of revenue. So these are all the revenue challenges when we talk about battery and storage system. So what are the really motivation towards the battery and storage system? So because now everybody is interested in installing the battery and storage system, because it will form the grid and it will support the grid, that it will improve the strength of the grid. These are all the terms that are there in the market. So what exactly that creating that requirement? So this is mainly because when it comes to Paris Agreement, all the countries have signed there for the carbon neutrality. So for that all the countries are moving towards the renewable energy grid. So for that, they're installing the PV and wind energy systems so that they are penetrating more amount of energy into the conventional grid. So if you see the globally PV installed in gigawatt, so 655 gigawatts has been installed in all the grids. So that's a very huge. And also, if you see the total global battery and storage installed, that is 173 gigawatt hour. So if you see the total global energy demand is 9,057 gigawatt. So that is total installed energy capacity, total installed power capacity. So in that, 18% accounts for the solar. So when we penetrate more amount of energy into the conventional grid, the grid will become very weak. So this is one of the most important driving factor towards the energy battery energy storage. So when it getting weak, so who will make it strong? So that's a battery energy storage. It will form the grid and it will make the system strong. And another motivation towards its trend is, so the levelized cost of the energy of the PV is getting decreasing. That is leading to installation of more PV into the systems, and also the levelized cost of energy of the BESS is trending still decreasing. So that is also motivating towards the battery energy storage system when compared with other energy storage like pumped hydro energy storage, or maybe some other hydrogen storages. So with this battery energy storage, so the main technology we'll get is grid farming. So with that, with grid farming, it is definitely support electricity grid from various aspects, and it will provide it will behave like a conventional synchronous generator, so that it will replace the conventional synchronous generator to make the grid much more stronger. So let's see what are the other things. So when we say battery energy storage system, mostly people it demands the more features that we can get through by operating it in a grid forming stage. So if you see this figure, so this is the system stability limit. So once we penetrate wind or solar, if it is penetration is 30%, so the stability of the system will close to the edge of the stability. If it is accounts 50%, so this is the grid following. So if you mostly PV or wind will follow the grid. So if you increase up to 40%, so it will reach its stability limits and it will try the system become unstable. So even if we improve the grid following, so that we can penetrate some amount of energy into the grid. So however, still it is under unstable region. So once we introduce the grid farming, so that we can go for 100% renewables, 100% penetration we can achieve. So this is the combination of grid following as well as the grid farming. That means the solar as well as and the battery energy storage system, or maybe other wind energy penetration. So these are the some of the grid codes, European grid codes. They will talk about all these kind of conditions. And also some of the countries, they developed grid forming codes. So China, UK and USA, Australia has released recent guidelines for the grid forming, how to operate, how to connect with the grid, and what are the requirements for each. And you can follow these grid forming codes so that you will get all the details. And also to meeting the grid codes is very important as an industry. So Huawei has performed all the tests and perfectly met these standards, as well as in fact about those standards. And also it has tested all its technologies SCR below 2. And also there are some use case scenarios that has been these are the real environment tested SCR. So in the simulation as well as in the real-time experimentation, that much more test has been performed. So these are the commercial battery energy storage adopts grid farming to enhance the system strength. So there is still a very good research area if somebody wants to initiate, that is quantifying the grid strength using grid farming as well as the grid following. So this is really a good research area, so that someone can concentrate on this one. So here you are seeing that these are the commercial battery energy storage system that deployed in on field for especially to enhance the grid strength. So let's see what are the solutions really. So we talk about what are the challenges, that is a safety challenge. One we had a talk, and also the revenue challenges we had talk about. So what really solution will meet this these challenges, will encounter these challenges, what are the real battery energy storage solutions, and what all its key features, we can go through that. And so on later we'll have a tour virtual tour towards the battery energy storage solution. So when we say the solution is a smart string battery energy storage system, so when we compare with industry standard battery storage system, which has higher round trip efficiency, which will increase the revenue of the battery energy storage, and it will discharge 2% more capacity. So this I will tell you how it will discharge 2% more capacity when it will compare with existing industry battery energy storage, because the existing standard battery energy storage, they don't have pack optimizers, though they do rack optimizers and container optimizers only. And also the constant power it will deliver. So when the SOC is very low, so if it requires the amount of power that to be discharged, so the battery has to deliver the constant power, so it should not reduce, so until it's fully discharged. And also availability should be more than 99%, because so the availability effect, so that will directly affect the revenues. So this is very much important. So this is the industry leading availability that by the Huawei. So SOC calibration will be done automatically by the AI and ML integrated algorithm that will be put by the Huawei. So with this, the total revenue will be saved per an 100 megawatt hour plant. So for coming to the stability of the grid aspects, so this will provide 3 times reactive power to the system, so that it will support the short circuit capacity of the system to improve its strength, and that is more far better than. And this one is can be adjusted based on the grid requirements as well as the grid operator's requirement. And also it will respond for abnormal response, that may be a frequency event or it requires inertia response. So it will respond from 5 milliseconds to 10 milliseconds, so which is industry leading response time. And also it will suppress the subsynchronous oscillations. So when we inject power into the grid, so there will be oscillations in the power, so which need to be suppressed, otherwise system will going into instability region. So it has capability of suppressing the power oscillations from 0.1 to 100 Hz. So there are some other industry battery energy storage system, the lack of these facilities. And also at the time of energization, so sometimes BS battery energy storage will go into maintenance. At that time of again at the time of reconnection, so the transformer need to be energized. At that time it will draw huge amount of inrush currents. So that time, if the battery energy storage is unable to provide those kind of energy, so that leads to a damage in the system. So here the transformers can be energized up to 150% when compared with other things. And also it has black start at gigawatt level. So gigawatt level means 1000 megawatts. So when you talk about a 1000 megawatt level plant, there are thousands of inverters, all will start at a time, so that the black start will it can reach up to rated voltage within the minutes. So this is one of the very biggest advantage. And when we talk about the safety challenge, so till now whatever the features that will shown, it will encounter the revenue challenges as well as grid stability challenges. So coming to the safety challenges that will be encountered when by incorporating the protection from cell to the grid level. So there is an algorithm that has been battery management system, monitoring system, which will monitor each and every cell. So if any abnormalities or alarms comes, immediately it will take decision and it will stop to discharge, and it will take or it will disconnect from the system to make the entire system operate safely. And also other full life cycle other safety features, that is design structure, so which is properly packed in a container, so so that the design will be optimal, and the energy and heat distribution will be very much optimal inside the container. So these are all the features, and also this is the overview of the solution. So we can discuss these features in further details. So when we say the optimal LCOE, that is levelized cost of storage. So when we say levelized cost of storage, that means the total amount of energy produced by a battery and storage of its lifetime divided by all total costs. That includes capital expenditure, operation and maintenance cost, and everything. So this will coming to BSS, it has been demonstrated on field, so which is the lowest ever. So that is the one of the advantage here. So when we say the grid side battery and storage, so peak regulation and frequency modulation, the real challenge is inconsistent battery, that is inconsistency of the battery and low usable capacity and short constant power output time. These are the challenges faced by the existing central solutions. So when we say hybrid, that is energy storage is combined with PV, so these are the challenges. So the coordination between the PV and energy storage system. So when we talk about the combination of wind and energy storage system, so here there will be the problem with anti-corrosion performance that needs support coastal installations. So these are the challenges. So for all these, the one-stop solution is PV and energy storage solution, that smart string energy storage solution. So which has higher capacities of with a small container. So this container will have 4.0 megawatt hour capacity, and which will use the smart power conversion. PCS is the power conversion system. 213 KTL, that is 213 kilowatt power conversion system. So with a smart transformer station, so it will connect at 33 kV level. And then it will be stepped up to 132 and then going to the grid. So this remaining energy management system will go into the PV, so that it can coordinate properly. And also, so by using this solution, we already discussed, it has above 90% round trip efficiency. That is much market trending one. And it has a constant power output, that from SOC from 0 to 100%. So these are all the features that we can have. And also, once the energy battery energy storage system forms the grid forming technology, so it will support the voltage stability and frequency stability and also the angle stability. So these are all the features. So let's go into the other details. So how it will deliver excess of energy when compared with markets. So let me explain the thing. For example, so we know battery packs, battery racks. So if you put an optimizer, these battery packs, so while discharging each and every battery, each and every cell, or in each and every battery pack, they don't have similar characteristics. Sometimes one battery cell or one battery pack may discharge more compared with other. So that time, when we discharge it to low levels, some of the battery pack may hit the lower level. So even if the other battery packs have energy to discharge, so because of hitting lower level of one battery pack, will stop you discharging. So if you discharge further, so that leads to a damage of the battery pack. So you can see the different kinds of charging and discharging. So that may leads to the problematic kind of things. See here. So one has reached, for charging, one has reached 100%. So other packs is still, there is a room to charge. So but if you forcefully charge those battery packs, so that will damage the battery system. So once we, if you see this battery pack optimizer solution, so it will monitor each and every cell, and it will make all the packs to be charged simultaneously. If anything is charged more, it will limit or it will reduce its currents to that. So everything will charge simultaneously and charge simultaneously, so that it can charge from 0 to 100%, it can discharge from 100% to 0. So this is all the highest feature of the battery pack, battery optimizer pack. So this will yields more amount of energy. For example, if you take 1 gigawatt of power plant, so if it is storing the energy, so this pack optimizer will account 5% of energy, will improve the 5% of battery energy storage. So that means we will have, during charging time, we will have 25 megawatt extra room to charge the more energy. At the time of discharge, we will have 25 megawatt of energy to discharge when we account for 1 gigawatt of plant. So this is the beauty of this one. So when we talk about other features, so black start, when we do black start, when there is no grid and blackout occurs, we required some power to power the nearby power stations to restore its power. So that time the black start is required. So it has very great advantage that thousands of inverters can start simultaneously a black start and reach its actual rated voltage within the minutes. So at the gigawatt level. So this can provide sufficient room to the existing power stations so to restore the power very fastly. This will reduce the grid recovery time as well. So when it comes to the grid farming, there are many features. So it will behave like virtual synchronous machine. So it will mimic its behavior like a traditional power plant. So and it will provide different features, and it has different features with high precision of voltage detection, high precision of frequency detection, and high precision of phase detection to participate in these events. That is a voltage regulation event, frequency regulation event, and also phase modification events when it requires, and also the phase adjustment. So these are the features, real features of the grid farming battery and storage system. So it will do a seamless from on-grid and off-grid. When we talk about the grid farming, we can talk about grid-connected grid farming as well as islanded grid farming. So both are very much important. So don't be confused between two. So this is it has a feature that it can seamlessly convert from off-grid to on-grid, on-grid to off-grid. So without any dynamically changes in the system. So let's talk about the capex saving. So this will improve the round efficiency up to 90% because of its pack optimizers and everything. So it will further increases, and also the system configuration itself will save some of the capital expenditure, because the distance between the converter and the station transformer, so we'll save the cable length as well. We'll save a lot of the cable lengths, and also the distance between energy storage and smart pieces, that is inverters, will save a lot of cable lengths. That will really save the capital expenditure. So the system architecture or configuration itself, it's optimal one to save the capital expenditure. These are all encounters these revenue challenges. And also when it comes to the real safety of the BS solution, it has 4-layer proactive safety levels. So the safety level is from the cell level to the pack level, and also there is a safety to safeguard from the grid level events. So there is a system level safety, that is 2-level passive isolation. So that will used by the that will protected by the fuse protection, and as well as the circuit breaker protection. So whenever the battery management system detects at the battery pack level any abnormalities, so it will try to fuse, if the fuse is not working, the secondary level, so that the circuit breaker will act. So after from the pack level, so it will comes to rack. So different packs will be make it as a rack. So then it comes from the rack level protection. So then it will comes to the container level. So if any faults that initiates from the grid side, so it will disconnect so that it can protect from those faults, especially during HVRT. So that is high voltage that comes, that will affect the PCS performance. So at that time, so if the battery and storage system is almost discharged, maybe at SOC level 5 or 10%. So if it is at the discharging function, if any HVRT comes, that traditional or industry battery and storage system, there will be backfeed towards battery and storage system. So that really a big problem with the battery and storage system, that will really affect the performance of the converter as well. So these are the protection, various levels of protection with the storage system. So when we talk about the safety, this is the total safety that cell to grid safety capabilities. So the cell and then pack and then rack, so and then system and grid. So this is all proper safety has been aligned in a such a way that so that the entire system is very much safe for very harsh environments, that for different environments, like if you consider European environment, there will be minus temperatures. So sometimes those temperatures will not leads to some ICs will not work. So the design happened in a such a way that it can work for minus temperatures to very harsh temperatures, like in Middle East temperatures, very hot temperatures also. So these are the design aspects and also safety aspects. And also some of the key safety standards that will followed by the Huawei is very stringent safety aspects. So first it will test the battery cell, so that is from a drop test. So if you drop a battery cell from 1 meter height, 2 meter height, so if it affects the battery characteristics or any explosion or any fire or any swell, so those kind of tests will be performed. So then only it can be validated and it can be discharged to a real environment. And another one is there will be a puncture into the battery. So if any puncture or if any stress on a battery, so that may leads to a swelling of the battery or explosion of the battery. So before going to be dispatched, so this will be tested. There will be a puncture through the battery. So you can see, so it's so you can see there will be a puncture. If it explodes, whether it is exploding, or it will be tested through various kind of testing methods. And also there will be short circuit test across the cell. So how much current is giving, and also how much time it is withstanding if any short circuit occurs, because sometimes if any short circuit occurs, we should have some time to respond, either battery management system or those kind of. So it has been tested properly, and also with very low resistance it has been tested. And also it has been tested with various environments, lithium precipitation, so those kind of tests. So after passing all these kind of tests, then only whoever believes that the battery cell can be discharged for various operations, maybe grid level storage or maybe different kind of storage. So we'll have a tour about the battery and storage towards all this one. So this is all we already had a talk about this one. When we talk about operational maintenance, because the Huawei is made all the automated things, so the maintenance cost, operational maintenance is very much limited. So when compared with other solutions, so let's have a small quick tour about the review about the Huawei battery solution. So this will be a smart.
I'm a brand new energy storage platform. In pursuit of a more reliable power system, I've been created to facilitate grid connection and boost the integration of renewable energy. My increasing capability in safety, grid forming, intelligence, efficiency reduces the levelized cost of electricity throughout my lifetime, delivering more benefits for various business models. I've been designed with safety at heart. It covers every part of energy storage system, including cells, battery packs, systems, and even grids. Each cell is strictly selected and must pass more than 100 rigorous tests. In case of thermal runaway, combustible gases are diverted and exhausted to prevent spreading among battery packs. Detection, exhaust, suppression, and relief measures are adopted to ensure system safety and reliability. The PCS dual-stage architecture integrates DC-DC and DC-AC modules. During high-voltage ride-through, this feature ensures stable operation of energy storage system and constant output of active power. Even in harsh environments, I can run reliably all the time. To cope with power fluctuations and balance the loads, I collaborate with partners closely to enhance the stability and reliability of the power system. Thanks to grid forming technology, gigawatt level synchronous grid forming can be achieved, and the entire grid can be black started with loads in minutes. By rapidly responding to voltage and frequency changes, I can effectively damp system oscillations, providing a stable voltage, frequency, and power angle. By implementing SCR full range grid forming, I consolidate the foundation for native stability. I keep improving my capabilities and use intelligent design to manage every part of the energy storage system. Automatic battery pack balancing and SOC calibration eliminate the need for on-site O&M. The entire energy storage system will keep multi-dimensional health diagnosis in real time. Real-time fault warnings help power plants run intelligently. I have been fully upgraded to support more business models. Refined management unlocks more energy and improves system utilization. With a higher round-trip efficiency and discharging energy at constant power regardless of the SOC. I am applicable to numerous business models and can operate reliably throughout my lifetime. I believe that on a global application perspective, I will support 100% integration and application of renewable energy to ensure long-term stability of the new power system. That is my mission.
Thank you. I hope this is not getting bored. So let's get into the slides further. So whoever believes in this, especially while developing the battery and storage system, so whoever believes various tests of validations before dispatching into any battery and storage system. For example, if you wants to construct a 100 megawatt battery and storage system, so these are the real kind of procedures it will follow. First, it will do design and simulation, various types of simulations through various validation platforms and everything. It will conduct all the possible tests that occurs in the real scenarios, and also it will validate its battery energy storage test lab, which is having a capability of testing 8.8 megawatt hour. So that's a real testing laboratory. It has been upgraded to 30 megawatt hour. So whatever the product or inverter or battery, or it will be tested in the field at the 30 megawatt hour level, and then will be discharged and will be tested for various all the applications in the real. So instead of only going for the simulations, it will test on the real as well. So, and at the time of delivery, it has all the offices in all the countries, so there won't be any obstacles while they're delivering. And also installation and commissions and also site acceptance, these are all compliance with the owner terms and conditions. So you can see, so mostly the simulation will be various softwares it will use to develop all the physical simulations, and also semi-physical simulations, that is with real-time digital simulators. So the PCS will be integrated with HL experimentations. So it will be embedded and it will be validated with semi-physical, and then it will be tested in real environment. That is, the lab has capacity of testing 30 megawatt hour of testing capabilities, LVRT and HVRT and V-grid test. Everything will be validated in real time with each and every inverter as well as each and every component, and it will be tested days and months together to validate its performance. Then it will be dispatched to the customers. This is the standard practice will be going with the Huawei. So we can see what are the installed battery and storage plants that has been done by the Huawei. So across the globe, there are many plants that has been installed. So here, one of the plant that is especially for the peak shaving in China, another plant that is for frequency modification. This is the frequency regulation in Singapore, which is around 40 megawatt hour. And also another plant It's a world's largest microgrid. So of 400 megawatt PV and 1.3 gigawatt hour. So that is 1300 megawatt hour battery and storage. So which is a islanded microgrid. There is no grid access. So which is 100% renewable, we can say. So that has been installed by the Huawei. So that is still currently in operational. So recently it came into operational. So on a totally, it has installed 15 gigawatt hour capacity of battery and storage system across the world. So we can have a tour up all the global level. This is things. So this is the world's largest microgrid that has been installed by the Huawei at the Red Sea in Saudi Arabia. I mean Saudi Arabia only currently. So this is the largest microgrid. So we can have a virtual tour towards this microgrid as well. So this is one of the project, and other projects. Yes, regarding this project only, it is we can say it is operating. The area it is operating is 100% renewables. Of total capacity is 1700 megawatts. So which is almost, which will supply very big cities like in India, like Bangalore, Hyderabad. So it's like very big islanded microgrid. So there is no, at the time of connection also there is no grid access. So with this project, the Huawei has proven that. So it's an optimal levelized cost of energy it has produced. So with that project, and also other projects that has been installed, very few of the projects we have a tour. So we'll have a small tour about the projects. So global all projects that has been installed.
When it comes to light, questions arise. Some questions have been put forward. People have more exploratory directions. Some questions have been answered. Then the world can harvest new development. How can photovoltaics become the driving force that lets the world achieve its goals? When energy and information collide, can we get the most out of new energy? If a PV controller has a brain, will it think and optimize itself? In the pursuit of light, our explorations span 40,000 kilometers, creating an ideal landscape for smart PV technologies. How can we generate electricity reliably in extreme environments? From extreme cold to extreme heat, we have overcome extreme temperatures and ensure reliable quality through rigorous tests, integrating intelligent technologies. With solar, we are creating a brain for smart PV plants. High-density power can improve electric energy production. Leading intelligent algorithm has overcome geomorphic restriction. Smart IV and CV fusion diagnosis simplifies operation and maintenance of scattered floating PV projects. Can PV help start a clean energy revolution in various industries? Solar farms bring hope for desert communities. Solar fishery breathes life into waters. Solar agriculture enriches the once barren mountains. On a plateau 4,600 meters high, we have created a world-class hydro-solar hybrid clean energy base. We are heading toward a low-carbon future with huge demand for PV and energy storage. Indeed, energy storage is indispensable in a new era of PV power generation. We offer efficient power conversion and safe energy storage and improve PV utilization through refined management, building a solid energy foundation for the future. The Red Sea project in Saudi Arabia is creating a city powered 100% by PV and energy storage and has become a beacon for the global PV industry. How does fusion solar help various industries achieve low carbon transformation through PV? PV is gradually replacing traditional thermal power to achieve energy conservation and emissions reduction. Commercial and industrial, smart PV solutions enable green and sustainable businesses. Smart PV helps revitalize old buildings, mixing tradition with modern living. Our products feature aesthetic design and flexible deployment, blending with the ancient architecture while meeting electricity needs. How can we ensure safe PV power supply in environments with strict safety requirements? Enhanced active arc protection, module-level fault location, and rapid shutdown help protect enterprise assets. Our products meet high safety requirements in various scenarios and comply with the highest safety standards in the industry. With frequent voltage fluctuations and power supply interruptions, how can PV pave the way for energy and ensure smooth business operations, stable electricity, and continuous energy supply? Ensure the efficient operation of users' businesses, building a high-speed energy highway. Can residential smart PV make our lifestyle and living environment greener? Fusion Solar residential smart PV solutions bring a green digital life with control of the entire house power information on one screen. How can we develop high-touch PV technologies? Our all-round customer services simplify product selection and delivery. How can we build a fully connected, intelligent home? With best-in-class technology, we create your dream carbon-negative home for a better quality of life. How can we light up more places around the world with technology? Smart PV lights up the night for better studying. Smart PV creates a more comfortable habitat for wild animals. Sunlight is the source of all life. Our coexistence with nature through unlimited clean energy is no longer an experiment or a distant idea. Whether it's a new city in the desert or a power plant on the plateau, the dark night is filled with light. Together with our partners, we embark on a green journey. The 40,000-kilometer PV scroll is unfolding. Fusion Solar, always forging ahead.
Let's have a small, quick, small tour towards world's largest microgrid. So I hope you enjoyed the video. So let's talk about much more about the standards. So still we have some time. So we can talk about the standards that are still there. I hope you can see my screen. So there are some other standards, safety standards for the energy storage systems. So yes. Yes, IEC, you can note down the standards numbers. Maybe in the later time you can search and go through all the standards. So IEC 62933. So these standards mostly talk about the electrical energy storage system, especially for grid applications. So in this, you may see the different subsections. That is 6293351. So that is recently updated one. So that's 51 is mostly talk about the safety consideration for the grid integrated energy storage, electrical energy storage systems, especially in general applications. So, and the second one is more, it will talk about grid integrated energy storage system, especially in electrochemical based system, that is battery manufacturing and how it by lithium ion thin films need to be there and insulation requirements, and it will talk about. And the third subsection will talk about unplanned performing the unplanned modification of the electrochemical based system. For example, if you already installed any battery energy storage system, so if you want to perform any other for example upgrading of that system, so what are the test procedures that need to be followed, these standard will speak about. Sometimes is there any changes in the system and we need to remove some of the energy storage part of the energy storage to replace other technology. So that times, for example, there are old energy storage technologies, that is lead acid batteries. So sometimes a part of will be replaced by the new technologies. So these are the standards that will be specified by the specified the guidelines to do those testing and methods and everything. And the fourth one is still under expected to deliver. It's still under progress. So these are all the standards. You can have you can go through all these standards, which will give the directions as well as the different guidelines to perform the different methods to validate the technologies. So I will quickly go through the things because the time is less. So yeah, I will discuss some of the things. Yeah, if you see, this is the plan. If you see this standard, so if you want to perform any unplanned action, so it need to be simulated and it need to be validated in various aspects. So after validating in various aspects, if everything is fine, then only we should go to a real environment. So original design and reuse purpose and installations. So these are, as per these standards, we need to go all these methods and testings, then only it can be allowed to do in the on field. So these are the procedures need to be followed by the various industries, not all the industries. So this is another the type of standards. So the main key takeaways of these standards is to learn is the safety requirements of the battery energy storage system, especially when we integrate with the grid energy storage systems. So this is what exactly the talk about. If you have any questions, you may ask. I hope it won't get bored.
Good evening,
Yes,
sir.
yes. Yes.
It was
Please.
really wonderful and eye-opening session, sir.
Yes.
Sir, can you suggest me any real-time battery management like open source software, sir?
Open source software, it's better to you go with your own. So you may have Texas or DSP boards. So you can better to implement in that one. It's like a kind of product you can launch from yourself. So you can use active balancing. That's a better one. So instead of going for the passive balancing always leads to power losses in the system. So it's better to use those kind of controllers. So that will be real-time based.
Okay. Thank you, sir.
Yes.
Hello, sir.
Yes.
Sir, I have one question relative to battery pack and each cell. As you told in some of the cells, percentage you have shown in one of the slides. There is
Yes.
slides that SOC and SOH, how it will be maintained and it should be measured. Any particular device is connected to each cell, or any from the main anode and cathode it should be connected?
So it's a communication data collecting entire all the pack. So there is a device for each and every pack which will collect entire data, and it will estimate the battery.
For each cell it will be connected, sir?
Yes. It's
What
all
is that?
designed.
What is that device, sir?
So that you should not disclose. That's industry thing.
Oh, okay.
So there is an algorithm to process everything which is equipped with AI and machine learning. So currently there are very high accurate algorithm to estimate SOC and battery parameters based on its voltage. So that is well equipped with machine learning. Advanced algorithms are already in real time.
And while charging also, each cell will be connected to same bus, or any separate bus while charging and discharging?
Same. The PCS will do charging and discharging. So it depends on the operation that need to be required at that time.
Okay, sir. Thank you, sir.
Yes. Thank you.
Any more questions?
Suresh sir, it is a very excellent presentation given by you. So I would like to stop your sharing so that we can open our videos and we will take a photograph with you, sir.
Okay.
So dear participants, kindly open your cameras so that I will take a photo. Thank you, dear participants, and you can. So actually, ASP has given one mandate such that you should definitely get half of the resource persons from industry and minimum 2 persons from foreign country. So we are really blessed. We have the resource person from foreign country, and he himself is a industrial person. So we feel very much comfortable speaking with him because he is our own colleague. And I request, sir, kindly allow our participants to communicate with you. I will, with your kind permission, with your kind permission, I will share your email ID also with all of our participants. So dear participants, this is the way you have to rise yourself from one level to another level. Sir is very, I'm sorry, sir, I'm telling you, sir is a very simple assistant professor in some autonomous college only, and sir has taken the step to take the PhD in IIT, and he just don't leave just like that degree. He has raised with that degree to go to abroad and try to settle in abroad. Now he is doing the second job in abroad now. So I feel very happy with him, and I request all the participants, those who wants to go abroad, you can take the help of sir. And especially Dubai is one of the best country for Indians because they will definitely take many people. Many of my colleagues first they leave to Dubai only, and then they try to go ahead with US and UK and some other countries. Even Singapore also, it's very needed to us and very needed to our arts. So my sincere request all participants, those who want to go abroad, so please take help of Suresh sir, and he will guide you how to go ahead with that, and what is the how he has secured, at least he will express with us. So I request all the participants kindly make use of his services. And coming to researchers, those who are researchers here, kindly take help of sir in going ahead with the microgrid, because he has given enormous explanation, and some way where he can't explain, that means he has shown the entire world tour of microgrids today. I feel very happy with your presentation, sir. You have shown entire world microgrid and world's largest microgrid also you have shown. So thank you so much for your kind cooperation. Still, I can give you some more time for all the participants. If you have any more doubts, you can speak with sir, and after that only we will close the session.
Sure.
Yes, if anyone
sir.
want to speak with sir, you can happily speak with him. Yes, anyone is interested to speak? Yes, yes, sir, please.
Sir, actually, to get, I have tried last from 3.5 years for going abroad. Not successful because maybe my actual experience from university, that is college experience. I have done my industrial experience. I have. Can I get any related to my proficiencies job like electrical engineer? Over there. Right now, I am doing my PhD in the JAIN University. Suresh sir, I thought that I am doing the same in your field as a battery energy storage devices, battery storage. In this same field, can I get a related job? Is it possible from your side?
You can connect through LinkedIn, sir. If anything I have or in my colleagues' companies, I will let you know the details.
Okay, sir. Okay, I have just now I have
no
your
issues,
detail in LinkedIn. Okay, sir.
I started the same way.
Okay, sir.
Yes.
Okay, sir. I will connect through mail also, sir, through you.
Sure.
Okay, thanks.
And feedback link was shared in the chat window. So yeah, definitely. I will share all resource persons' email ID. Maybe tonight I will share all email IDs and phone numbers. So no need to worry. And so feedback link is also shared in that. And please fill that feedback link. And today I thought of giving you 20 multiple choice questions, whatever we have completed till date. And maybe another 20 I will share you on the one day before the session, maybe 5th day. And 6th day is the real examination, and that will be conducted by AICT only. So please make sure that you should be prepared for the examination, and you should get 70% of marks. And attendance is also mandatory. Those who are filling the feedback form, I will give the attendance. And my sincere request would be, next coming resource persons are also industrial persons. Till date, we are covering very good industrial persons and very good academicians. So from tomorrow onwards, most people are from industry only. Please try to make use of their work, okay, what they are doing actually. And if you want to collaborate, you can collaborate. But my sincere request would be, whatever collaborations you want, you can speak with them personally, okay. So you can speak with the content what they are sharing here only, okay. This is my sincere request. And now after half an hour only, I will post this one of the Google form also, okay. That is the related to examination. You just make your try and keep it. No need to worry. And on the fifth day, I will share one more examination that will also contain 20 or 30 questions. So as the time given to us is 30 minutes only, so I can give you only 20 questions for your examination. You have to score 14 marks, correct? So this is the concept. So If you have any more doubts, you can contact us at any point of time through WhatsApp group, and even to directly sending mail also. So it's better to send mail, WhatsApp message directly to me, okay, so that I can immediately answer to you. So thank you so much, and Hana madam.
Sir.
Yeah, could you please help me if I left out anything, any announcements, and please give me concluding words, and please conclude.
Thank you so much.
Can I?
Thank you, Dr. Suresh. Your session was very insightful with a lot of visual images and videos, and that will help us to understand the real microgrid and the challenges that we face while integrating the battery energy storage system with the grid and the mitigation technology that is being adapted in Hawaii. So it has been clearly articulated. Thank you so much, sir, for joining today and for your sharing that valuable time with us. Thank you, sir. So dear participants, kindly join the further sessions on time, and we appreciate your cooperation in the future also. Thank you so much, sir.
Yes,
Thank
sir.
you, everyone. Yes, yes, sir.
Tell
Thank you, everyone, each and everyone, and the participant as well as the Kishore sir. He is my colleague. I know he is a very hardworking person. So still, it's a pleasure to interact with everyone. And also, if you need any help in choosing the research areas, I can help you out as well. So if you want to be in touch, you can be in touch with my email ID. So that will be shared by Kishore sir. So, and also thank you for everyone for your patience and listening and everything. Thank you so much.
Thank you, sir. Thank you so much.
Thank you all.
Yes, sir. Thank you so much. Dear participants, with this we are concluding third day of ATAL online FDP, and 3 more days are waiting for us. Okay, so please join at the same time with same links. Okay, we are not changing the links also, time also same, and 6th day timings will be changed, so that will be disclosed on 5th day only. Okay, that would be better, and even we have already shared the schedule also, that you can come to know. Okay, so thank you so much. And